I think we cannot hear you because you're muted. Hi. Hi, hello. Can you hear me?
Yes, I can hear you.
Great, great, great.
I am not sure why I am under the name of ESV step Suzhou. This should be. I come back.
Sure.
Hi, Fanmo, are you here?
Yeah, I'm here.
Thank you for taking over. So this was not responsive. Thank you for having additional duty. I appreciate that. This session is supposed to be hybrid. So I expect by now our Shanghai staff should be here under the name of host 1 and host 2, because there will be some offline audience.
Okay.
Will be joining from the Shanghai venue, but I don't see them. Maybe I can quickly call Karen.
Okay.
So Weiwen, you are connecting from the US, right?
Oh yes, I connected from US.
Yeah, okay. So, and you have 2 more speakers, right?
Right, I actually have 2 more speakers, yes.
Yeah, okay, I will be back and I will try to get our Shanghai staff on
Okay.
Zoom.
Okay, great. Sure.
Yeah, now I see some host.
Right.
Oh, okay. Hello.
Hey, can you hear us? I think they are still connecting to the audio.
Oh, yeah. Is there anyone in Shanghai venue? Can you say something? Can you hear us?
We can hear you.
So you have found the Santa Clara, right?
Yes, I recently moved to Santa Clara, so yeah.
Because actually you know that I cannot see your name. I just say your
Oh,
note. Yeah.
yeah, okay. Let me I don't know how to change it because
I think you can right click for your video, and then maybe you can change the rename.
my
Yeah.
video. Okay.
And if you right click, I think there is a rename.
Um, okay. Rename. Okay, great.
So are you from the sales department or EC department and SCU?
Yes, ECE department.
I see. I see.
Yeah. But in our school, this computer science department is much bigger than ECE.
I see. I see.
We share a lot of, courses.
For sure, you're very close to. I mean, to the companies, to the industry. I do believe there is a lot of demand for the computer
Yes,
science.
yeah, I mean, literally in the heart of Silicon Valley, and many of our graduate students are part-time students, and
I see.
they work for companies nearby. And
Right. Hi. Actually, we cannot hear from you. You are muted.
uh,
I mean from the live. Actually, they are muted.
Okay.
We can see you, but we cannot hear you. We cannot hear you.
I think over there, Professor Gu is there. Professor Gu, can you hear us? We can see you through the camera, host 2, but we cannot hear you. We are not sure if you can hear me. You can hear us. So during the dry run, it was okay, but during the dry run, we actually have 2 camera views, host 1 and host 2.
Oh, really?
Yes, I heard that one is for offline speaker. I'm not sure if this is not the case in this session, but they prepared 2 cameras actually. Not sure. I mean, in gather room, maybe I can. Host 2 is here. Oh, yes, switch to Zhu. Maybe that is from Shanghai. Oh, great.
Great.
Hi, can you hear us? Can you hear us, Shanghai?
Hi. Yeah, actually, I think we can hear you.
you hear us, Shanghai?
Yeah.
Okay,
Yeah.
Great.
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 让它仰角怎么调一下呀？是要再更长一点吗？还是可以更短一点？
Jose, do you think that we should wait for a couple of minutes before starting? I think maybe people were streaming at this moment.
I think if Shanghai room is ready, then we can start. People are joining in, so you want to wait for a couple of more minutes?
Sure. Yeah, actually, I think we can do that. As far as I can tell, that the Shanghai Zoom is also have some people come in and come out. So.
Hi, Weiwen.
Hi, Dr. Gu.
Hi, Tom. I think we are ready.
Okay, great.
好像没有人。这都是捋放在后面的。
Actually, I see a lot of people online in the gathering town, but actually they didn't enter the Zoom.
Then let me quickly make an announcement in Gather.
Sure.
Let me quickly get out and I will make a verbal announcement to the people in the room.
Sure, sounds great. So, Hosaki, do you think that it is time for us to start? If so, maybe we can start either way. You are muted. We cannot hear you.
Okay. Yes, I think we can get started. So can I introduce you?
Sure, please. Thank you.
Okay, thank you for joining. So let me introduce Dr. Jiang. So Dr. Jiang is currently with George Mason University. He studied there in 2021. Before that, he was a postdoctoral researcher at the University of Notre Dame, and he received his PhD degree from Chongqing University. And he won a lot of important awards, including the Best Paper Award from IEEE TCAT and ICCD and MVMSA. Other than this, he won a lot of awards from ASPDAC and top winning award at IEEE Services Hackathon. And he is known for the first co-design framework called QuantumFlow. I think this is the main topic of this tutorial. And he published a paper in Nature Communication about this. He's very well known for this topic. And let's welcome our speaker. And
Thank you for the chair for the kind introduction. And before we move on, actually, I would like to let you know this resource page. And you can see here is a website. Actually, this is designed for this purpose for this tutorial. And if you just click it, you just scan the QR code, you can also arrive this page. So just click it, and also you will open the website for this tutorial. And we have a lot of resources here, like the slides, or also I think this is not updated, and also a lot of code lab, so that you can run it on site. And also we have the paper on and also hands-on website and platform. So you can find a lot of information here, and also a lot of resources here. Okay, so in later, for the audience join us later, actually I will also show this website during this presentation, during this tutorial. But for now, if you guys have the access to the website, actually you can start now. So okay, let's move on to today's tutorial. Actually, this the tutorial is on the title of the tutorial is on the quantum flow and vaccine. Actually, this is our most recent work. And here is the agenda. Actually, we will split our tutorial in 4 sessions. And the first session, we will do the opening and introduce the background, why we need to consider such kind of problem, and also what is the important thing for the quantum and machine, the combination of quantum and machine learning. And in the second session, we will introduce the quantum flow. That is a co-design framework our chair just introduced, which was published in the Nature Communications last year. And in the third session, we will introduce most of our recent work on the quantum neural network comparison. This is the first comparison framework to support the quantum neural network optimization. And the fourth session will be the vaccine. Actually, that is a visualization tool for to analyze the noise in the quantum computing. Okay, so let's enter our first session. That will be our opening. And before that, actually, I want to introduce myself a little bit. My name is Weiwen Jiang, and I'm currently an assistant professor at George Mason University. And here is my education background. I graduated from Chongqing University, and my advisor is Professor Edwin Sun. And during the last 2 years of my PhD, I joined the University of Pittsburgh to conduct research. And my advisor at Pittsburgh is Dr. Jintong Hu. And after I graduated for my PhD, then I joined Notre Dame for 2 years postdoc. And that period, my PI is Dr. Yi Yushi. And during that period, my main research focus is on the hardware and software co-design. As you can see in the slides, actually, we built up a full stack to support the co-design for the machine learning system. And on the most left-hand side, that is a co-design framework that we built to provide to introduce the co-design philosophy in the design of machine learning system. And this work obtained the Best Paper Award and the IEEE TCAT. And also in a full stack, actually, you can see that we involved different layers from the hardware algorithm to the applications. And on the hardware level, we target on the FPGA, ASIC, and the computing in memory architectures. And in this work, actually, we obtained a lot of base paper nominations in DEC, ESWeek, and also the SP DEC. So today, actually, I'm not talking about the research on this channel. I believe we have another tutorial hosted by Dr. Jintong Hu, which is more focused on the hardware and software code design for the classical computing system. But for today, we are more focused on the quantum learning in this tutorial. We are going to see what is our most recent breakthrough on the quantum learning. So we can leverage the new computing platform to support the machine learning algorithms. Okay, so at the very first of the tutorial, I would like to highlight our goal for the quantum learning. And the first one is that we are targeting on different group of peoples. And the first group is the quantum neural network researchers. Actually, we want to ask the question, what will be the practical way to approach into the quantum advantage? You know that actually today, actually we have a lot of quantum computers, but people are trying to design algorithms to see how can we achieve quantum advantage. This is very important because you know that compared with the classic computing platforms, actually quantum computing has a lot of advantages like a high parallelism. But how to exploit this advantage to achieve the real quantum advantage actually itself is a open topic. And so for this research, actually for this line of researchers, actually what we want to do is that we want to find a practical way to approach into the quantum advantage by using the quantum neural network application. And the solution here is that we propose to have an algorithm compiler device co-design so that we can leverage the high parallelism in the quantum computing. And our second target group user is for the quantum computer users. And you know, so for today's quantum computing, there are a lot of limitations. Like it has the qubits itself has high noise, and therefore, how can we get understand of the current status of our quantum computers actually itself is not a very straightforward task. So the solution we provide in this tutorial is a visualization tool so that we can visualize, we can see the status of our quantum system so that it can help the designers, it can help the quantum users to have the sense which quantum computer is most fit for our applications. And for our third group of users, that will be for everyone who want to leverage the quantum computing for their own task. Actually, the question we want to ask is that how can we enable everyone to use the quantum learning techniques? And also our solution here will be the quantum learning democratization. Actually, we want to provide the automation tools for to support the quantum learning democratization. So before going further, actually in the opening session, actually we will go through details from the classic computing to the quantum computing, and also we want to give you the motivation why we want to conduct the research on the quantum machine learning field. So the very first question we want to ask is that what is the quantum democratization? And actually, this idea is driven from the classical AI. And as you know, there is a term of the classical AI democratization. And this term was proposed by Fei Li from Google in 2017. And the main purpose of the AI democratization is to enable everyone to have the opportunity to use AI. And let's consider some scenarios. For example, in the medical AI scenario, actually there are a lot of there are a lot of things that our computing can provide some advantage for the user, for the doctors, like the AR and the VR in surgery. And the detailed task that our machine learning can help is like the segmentation. Actually, for the AI, it can learn some features from our figure and then conduct the segmentation task on the figure. So for this, for example, this figure demonstrates that when we have you know that for the COVID, actually when we have the CT scan image, when we want to analyze the CT scan image, actually the AI can help us to do the segmentation, so that the red ones marked pixels indicate that how the abnormal section of our lung. So in this case, actually, why we need to add democratization? Actually, the very direct answer is that you can think in such kind of scenario, it is even impossible to let the doctors to design the neural network by themselves. They have the expertise in the medical area, but they do not have the expertise in the machine learning. So if in order to let this group of people to use AI, actually we need to provide a very easy tool for them to design the neural network. So in order to achieve this goal, Google's initial contribution is on the new architecture search. And for this problem, we are given a data set like the image from the medical image from the hospital. And our objective is that we want to search for the neural network, which is without the human involvement. And also we want to maximize the accuracy on the given data set. And so these are our two objectives. And our output will be a neural network architecture. And so people designed such kind of optimization loop to control the optimization of neural network. Yeah. So, okay, I see some background voice. Okay, so maybe we can continue. So you can see in 2017, actually Google proposed such kind of new architecture. Actually, there is a controller marked as red in this figure. This component will control the optimization process. And what we will, I know where the background come from. Okay, so what we can see here is that so the controller will control the optimization loop, and you can see for each time actually the controller will sample a new architecture with a probability p, and such kind of neural network architecture will be trained to obtain the accuracy. Then the accuracy will be fed back to the controller to update the controller, so that we expect the optimization can be controlled by the RNN in the controller to do such kind of process. However, when we want to deploy the neural network onto the real hardware devices, actually, we encounter a problem. That is, the new architecture identified by NASA will be too huge to achieve high accuracy, but our hardware has limitations like the resource limitations. So our contribution on this field is that we propose a network and accelerator co-design. And our objective is not only maximize the accuracy, but also we want to maximize the hardware efficiency. And our output will no longer be a single neural network architecture, but will also be a pair of neural network and hardware design. And our initial work observes that there is a missing link between the new architecture search space and the hardware design space. So that we propose the first framework to complete such kind of thing, so that we can simultaneously explore the new architecture and the hardware design. And as you can see in this figure, actually the most important thing in both framework will be the automation. So in order to achieve the AI democratization, actually the automation will be the key. And also, after years of research on the neural network architecture search for the hardware, actually we built up a co-design stack for the new architectures. At the beginning, people are asking the question, what will be the best new architecture for the hardware, like the FPGAs, and also what will be the best hardware design to support the neural networks. So for the first question, people designed the network exploration to conduct the network architecture search. And on the hardware side, actually, people designed the FPGA architectures so that they can do the acceleration task on the hardware. And also in the middle layer, actually, we have the library to support the people to easily program the neural networks onto the hardware side. And also we have other model optimization techniques like the pruning and quantization to support the network compression. And the last, actually, you know, for the hardware side, we have more and more complicated tasks like the mapping and the scheduling. And at the end of the day, we find that there is a missing link between the optimization of the neural network architecture side and also the optimization of the hardware side. So the code design framework was proposed. So for now, actually, we see a very good picture for the classic computing. We have the different design component, and also we have a design stack to support deploying the neural network onto the hardware. But what will be the problem? What will be the bottleneck in the classic computing? So in these two figures, actually, we want to demonstrate, we want to give you the motivation why the classic computing meets the bottleneck, and we need a new platform to support the machine learning stuff. So in the first figure, the x-axis represents the top 5 error, and the y-axis represents the number of operations. As you can see, with the aim of low error rate, actually the size of the neural network grows exponentially. However, for our classic computing platforms, on the other hand, on the right-hand side figure, we can see that with the end of the Moore's law, the performance density almost stopped increasing. Therefore, it creates a gap between the demand of the computing for the machine learning algorithms and also the supply of the hardware from our hardware side. And so let's go back to see our driven application, the medical application. You can see that for today's AI, it is really easy for us to handle the radiology imaging, like the CT scan, like the MRI, the X-ray. Actually, the input size of this task, this application is merely 100 to 200 megabytes. On the other hand, if we want to solve some problem like the pathology imaging, actually the input size will grow exponentially. Actually, you can see for this task, actually we have some application having the size of input data which exceed 1,000 gigabytes. So that is reached 1 terabyte. Therefore, in order to solve this problem with such kind of big input data, actually the current computing platform has the limitation, and also we made the bottlenecks. So so for this slide, actually we want to demonstrate that in some cases, actually the task that is impossible in the classic computing, but it may be possible in the quantum computing. As you can see from this figure, each triangle represents one quantum computer from the IBM, and the x-axis represents the time, that is the timeline. And you can see that along with the timeline, the quantum computers also increase sharply. And today we have a quantum computer with 127 qubits. And also this block represents the quantum computer from Google and from other places. And an important observation here is that when we want to simulate the task on the quantum computing, actually the capacity of the classic simulation is stopped at 47 qubits. That means if we exceed this threshold, it is really hard for the classic computing to simulate the quantum computing. But you can see that today we have a quantum computer with more than 100 qubits. Therefore, this simply demonstrates that for some tasks that is impossible to simulate it in the classical world, actually it is possible to implement by the quantum computing. And driven by this, actually, we are thinking about can we apply the neural network onto the quantum computing platforms, and also we are trying to answer the very initial questions: what will be the best neural network architecture for the quantum computing, and also how can we design the quantum computing so that we can obtain the best performance for the neural network to support the neural network. And in order to answer these questions, we also need a library. But part of the experience from the classic computing, we believe that a code design framework will be the fundamentals, and we propose a QuantumFlow to do such kind of thing. And also for the question about what will be the best neural network architecture for the quantum computing, actually we also do the exploration on the neural networks, and we propose the QF mixer component to support this task. And also, for the hardware side, we also need to cover some challenges from the hardware from the quantum computing, and we proposed the QF robust NN, which is a device-aware design. And we have the library QFN to support the programming. And finally, we are also doing some optimization on the quantum neural networks, that is the network compression CompVQC. Okay, so in the following, I will briefly introduce the sessions. Actually, for the session 2, we will introduce the QuantumFlow co-design framework in detail, and the QuantumFlow framework gave us the hope that you can see that we can reduce the complexity of the basic neural operation from order of n to on the classic computers to order of polynomial log n on the quantum computers. And in the third session, we will introduce our most recent research on the optimization of quantum neural network, that is the quantum neural network compression. And our result demonstrates that we can reduce compiled circuit length for more than 2 times with less than 1% accuracy loss. And finally, we will, in our fourth session, actually, we will introduce a VACSEN, that is a visualization tool for noise in the quantum computing. And this work also has already been accepted by the VIS, and also it will be presented then in October, very soon. Okay, so this is our first session. I'm not very sure whether we have some questions. And if you have some logistic questions, please feel free to ask, and I can address it now. All right. So I will leverage this time to switch for our second session. So if there is no question from the audience, maybe we can move on to our second session, and this session where we will introduce a QuantumFlow co-design framework. And you can see from this figure, the hand side figure is the roadmap from the IBM to develop the quantum computers. And you can see that in 2019 we have the quantum computer with 27 qubits, but now we are at this position at Eagle quantum computer with more than 100 qubits. And so the first question is that what will be the use of this quantum bits? And so in this slide, we will show the difference between the classic bit and the quantum bit, also known as a qubit. So for the classic bit, it can be either represent 0 or 1 and 110. But for the qubit, actually you can see from this figure, actually we also have 2 states, 0 state and 1 state. But unlike the classic bit, we are operated all operations. We are at one time we are either in the 0 or 1. For the quantum computer, for the quantum bits, actually we can hold these 2 states at the same time. So we have 0 state and 1 state instead of all one state. And you can see here, for each state, we will associate an amplitude to the state. Like in this example, we associate amplitude A0 to state 0 and A1 to state 1. And the property here is that the summation of the square of both of all states will be 100. Therefore, you can regard the amplitude is related to the probability to obtain 0, and also A1 is the probability to obtain the state 1. And when we do the mirror out, actually the A0 square and the A1 square represent the probabilities for our quantum system to reach to one state at the end of the day. And we also introduced that the constraint here is that the summation of all probability will be 1. And so for the representation, you can see that we can represent the 1 qubit like in this way, the psi equal to A0 times 0 state. This is also known as a bucket state. So we have the K0 plus A1 times K1. And also we can represent this 2 amplitude in a vector way, so that we can easily to apply the the linear algebra to operate the state of the qubits. So for these two representation here, they are equivalent. So we can use either way to represent the one qubit. And for the initial state, actually the qubit will be initialized as a 0 state. That means A0 will be 1, and also the A1 will be 0. So for this state, it is also known as a ground state. And if we and also you can see that for the you can see then for such kind of 0 states, the vector representation will be 1 and 0 because A0 is equal to 1. And for now, we know the representation of 1 bit. So what is the magic of the quantum computers? Actually, it is not based on the single qubit. Actually, it is based on multiple qubits. As you can see in this slide, for our classical bits, actually, if we have multiple classical bits, like the 2 classical bits, it can only represent a number with which is composed of 2 bits, like 0, 0, 0, or 0, 0, 1, or 1, 0, or 1, 1. On the other hand, if we have 2 qubits, actually we can assign the amplitude to each state, and therefore at this moment we will represent 4 states at the same time. When we extend such kind of system to n qubits, actually the n qubit system, quantum system, can represent the 2 to the power of n values, and each value is corresponding to the amplitude. And in the right-hand side of the slide, we demonstrate that actually for the for such kind of quantum bit with multiple qubit system, actually we can always use we can also use such kind of formulation to represent the multiple qubits. And you can see here the amplitude itself is still related to the probability. And if you do a simple math here, we can obtain the C000 square is equal to A0 square times B0 square. And if we want to calculate the C000, it will eventually equal to A0 times B0. And such kind of operation is exactly equivalent to the tensor product. So that when we try to combine the multiple qubits, actually the fundamental mathematical operation will be the tensor product. Actually, we can use for example, for here, if the Q0 is represented by the vector A0 and A1, and the Q1 is represented by the vector B0 and B1, and after that, if we combine these 2 qubits, actually we can obtain a 4 by 1 vector, and the value C0 is equal to A0 times B0, and the C01 is equal to A0 times B1, and so on and so forth. So I think this is the basic, very fundamental thing when we consider multiple qubits. How can we calculate the result of multiple qubits? And so for now, we see the data. How can we hold the data in the quantum computing? And the next question is that how can we do the operation on the quantum computers? So in this slide, the left-hand side is our classical logical gates, and the right-hand side is our quantum logical gate. So the basic idea is that we will like the classic computing, we will apply the quantum gate to the qubits so that we can operate the qubit the status of the qubits. And I think you were very familiar with the classical stuff. If we have a NOT gate, actually it will follow the truth table in the below. And if the input is 0, our output will be 1. If the input is 1, our output will be 0. So for the quantum computing, actually for 19, it will represent 1 qubit, and before the gate X, actually we also have the state. We denote it as state A, and at the end of the, on the output of X, actually we have the state of Y. So the transition, we still have the state transition in the quantum computing, and also the operator here is changed from the NOT gate, the classic NOT gate, to the quantum logical gate, like the X gate. So the operation here is that we will apply the multiplication between X and the state to do the transition. And you can see that if you still remember, for each quantum state, it is represented by the vector, right? So if we want to do the transition now, what we can have is that we will do the matrix multiply the vector, and the final result will still be the vector. So this is a similarity between the classical logic and also the quantum logic. And in the next step, we will see some difference between the classical logic and the quantum logic. Therefore, it will help us to think actually we need a totally different design for the quantum computing. And as you can see in the left-hand side, if we want to apply the input to multiple gates, actually it is really easy for us to drag another line so that we can apply the input to the classical gate. On the other hand, we cannot do the same stuff on the quantum qubits. Actually, we cannot do the copy and paste on the quantum computing. And in the following, I will give you some examples how the gate operated on the qubits. And the first example is on the NOT gate, also known as the X gate. At the beginning, we have the state 1 and 0 that is represented as the 0 state. And if we apply the X gate onto the 0 state, we will do the multiplication between the matrix that is related to the X gate. And you can see our output will change from 1 0 to 0 1. Therefore, you know that the 1 0 is related to the 0 state, and 0 1 is related to 1 state. So this is simply equivalent as a NOT gate in our classic computing. And we have other gates like the Z gate, and the operation will be similar. And for the Z gates, actually we will change the amplitude of our second element in the qubits. And superposition is a very one of the very important concept in the quantum computing. And we have the Hadamard gate help us to change the state from 1 0. This is 0 state to 1 1. So for now, you can see that the quantum system are in the state actually for each state, 0 state and 1 state, both of them have the amplitudes. So we call it the qubits in such kind of state is in the superposition. And also we have the U gate help us to convert the qubits into the superposition state. And also, if we consider multiple qubits as we introduced, actually the qubits itself is conducted the tensor product to compose a new state with more amplitudes. And for here, actually we can see that if we the operators like the Hadamard gate, if we operate them in parallel, actually we also we can also use the tensor product to create the multiple qubit gate. And finally, we can also follow the previous state transition operations to transit our state from the 0 0 state to the superposition states. And finally, I want to introduce some concepts on the single qubit gates. Actually, like our classic computing, we have the big end and the little end. Actually, in our quantum computing, we also have the big end and the little end. So for the IBM Qiskit and also the Quick from the Google, actually they will read such kind of circuit from the bottom to the top. So then for such kind of system, they will regard as 1 0 state, like demonstrated here. And when we compose the gates, actually the tensor product will also follow the order from the bottom to the top. On the other hand, for a more natural way is the encoding used in the wiki quantum gate, and also it will be applied in this tutorial. And we will regard such kind of system as the state of 0 1. And also when we do the composition of two gates, actually we will follow the order from top to bottom. And now we are going to see another type of gate. So that is not for the single qubit gate, that is not only control one single qubit. So we are now have the qubits to directly control multiple qubits. As you can see here, we have the C0 gate. So the C0 gate is the control NOT gate, and the concept is that if the first qubit is in the state of 1, it will apply a NOT gate or X gate on the second qubit. And in this case, if you can see at the beginning, we have the state of 1, 0. After we complete such kind of NOT gates, the second qubit will be flipped for the state, so that we will have the 1, 1 state at the end of this circuit. And also we have the control Z gate, so it will change the phase of our last amplitude. And now by using the previous introduced gate, the single qubit gate and the multiple qubit gate, the control NOT gate, actually we can make the qubit get into the entanglement state. As you can see in this figure, at the very beginning, we applied the X gate, so that the first gate will become the 1 state, and after we apply the control NOT gate, the second one will also be 1. And in this time, actually, these 2 qubits can still be represented by the 1 state tensor product 1 state, so they are still independent. However, if we apply the Hadamard gate at the beginning, you know that at this position, the gate will becomes like the 2 over. Like this with for each state it has amplitude, and when we apply a control NOT gate into such kind of 2 qubit system, actually the eventually result will help us to obtain such kind of result, and you can see only 0, 0 and 1, 1 has amplitude. So in this case, these 2 qubits are no longer independent. We cannot rewrite such kind of state using the tensor product, and we call such kind of state as as a qubit enter the entanglement state. And so for here, we provide the hands-on for the previous introduced gates, and also the single qubit gate and the multiple qubit gates, and so we provide both the GitHub and the code lamp codes, and also for all of the resources. If you are attend this session a little late, actually you can find the resources in this website, or you can just scan this QR code to arrive our website. So for now, what we can see is that actually, if we open it, actually we build the code lab, so that I know that maybe some of you are blocked by using Google, but for you who cannot access the code lab, maybe you will need to download the repo in our GitHub, so that you can run our code. On the other hand, if you have the access to Google, actually I do believe that you can directly go to the code lab, and here we can directly run the codes to install the library, and also import the library. After that, we can build up the X gates introduced in the tutorial, the Y gate and the Z gate, and also Hadamard gate and also U gate. And the Hadamard gate and the U gate will help us to enter the superposition, and also we see the 2 Hadamard gate on different qubits, and also we know that we can have the combination of different qubits. So we provide a lot of example in this tutorial, and if you want to know such kind of fundamental knowledge on the quantum computing, just feel free to check out this repo. And also we provide you the information how can we use the Hadamard gate and the control X gate to get into the entanglement state. As you can see for here, we have the first amplitude we have the first state has amplitude, and the last state has the amplitude, and the middle 2 state has no amplitudes. So in this case, the qubit system enters the superposition. All right, so for the audience, if you have any questions, you are feel free to leave the message on the chat, or for the on live audience, if you have questions, just feel free to interrupt me. That will be okay. So let's move on to the next part. So as you have already seen, there is a specific type of gate, that is the U gate. And for the U gate, you can see for this kind of gate, we are not simply change our state from 0 state to 1 state, that is a NOT gate, right? And for this gate, actually we have the parameters inside of the gate. So because why the name is U3 gate? That is because actually we have 3 parameters to control the qubits. As you can see, this will for example, if we are at the beginning, if we are in our ground state, that is 0 state. After we apply the U3 gate, our qubit state will turn into 1 point in our space. And for now, with the understanding of the U gate, the most important message I want to send here is that, so for the quantum gate, actually we can have some parameters in the quantum gate. And so now we are trying to talk about something about the quantum machine learning. Actually, there are 2 paths to achieve the quantum machine learning. And the first path is that we can use the variational quantum gate, also known as a parameterized quantum gate. So that is the gate. The quantum gate has the parameters. As you can see in this figure, actually for a typical quantum machine learning algorithm, we have the 3 stage to do the inference. The first stage is encoding. We want to encode the feature map to the qubits to the quantum system. And the second state is the variational quantum circuit. And you can see for this part of circuit, we use the quantum gate with the parameter theta. And this theta can be changed. So then we can, if we want to learn some feature from our input data, actually we can change the angle of this gate, so then we can perform different tasks. We can perform different functions. So this is very similar as our classical machine learning, because for the classical machine learning, we always want to train a neural network that can mimic a type of function. And so for here, the parameters, the trainable parameters, will no longer be the weights in our in the edge of the between the neurons. Actually, the parameter here will be the trainable parameter. The weight here will be the parameter inside the quantum gate. So the last stage is that we do the measurement, and after that, actually we can compare our result with our ground truth, and then we can optimize. We can apply an optimizer and do the update of the parameters, so that we can also approximate some function. And kind of know that such kind of update of parameters is conducted in the classic computing. So this paradigm is also known as a hybrid classic and the quantum paradigm for the quantum machine learning. And the pros of this kind of approach is it is very easy to implement, because we directly use the fundamental gates in the quantum computer. So that is a parameterized gate, like the U3 gate. And the problem for this kind of scheme is that on current intermediate scale of quantum devices, no works demonstrate that the performance of the quantum machine learning can beat the classical machine learning. And the major challenge is from the fundamental things, because you know that in the quantum computing, we have the matrix we have the matrix to represent the quantum the quantum gates, and the different quantum gates, actually their operation will always be the linear operation. So it lacks the nonlinearity in the quantum circuit. And also, you know that for the classical machine learning, the nonlinearity will be the very important thing to help us to obtain the high accuracy. So for the quantum computing, a very simple way to include the nonlinearity is that we add a lot of measurement in between of layers. But in this way, we will bring a lot of overhead to implement such kind of nonlinearity. So the second path is not directly use the quantum gate to become a trainable weights in the quantum circuit. Instead, we want to implement the neural network, the classic neural network, onto the quantum computer. So this is similar with our hardware accelerator design. So the idea for such kind of process is that we want to directly implement the same function on the hardware, like the FPGA or the quantum computing, so that we can have so for our quantum computers, we will have the same performance as the classical machine learning. But the question here is that how can we design the quantum circuit, and also is that possible for us to obtain any advantage in such kind of things? So in order to answer this question, I think the most fundamental question is that what will be the complexity? Also, this is related to the quantum advantage. And we checked in our classic computing. Actually, you know, we have the time complexity, we have the space complexity, but if we only consider the one type of complexity, actually we cannot describe the complexity of the system in a reasonable way. So let's see these two examples. If we want to describe the complexity of the of one neuron demonstrated in our left-hand side of the slides, actually you can see that if we only use one max, so this is represent the space, the computing resources is order of 1. And in this case, the time complexity will be order of n, because for each pair of the of our input and the weight, actually we will need to do one operation on the by using the max. And for the classic computing, if we have n max, actually we can reduce the time complexity to be order of 1, because all of this n operation can be conducted in parallel. However, the space complexity, that is our computing resources, will grow to order of n. And so you can observe that if we are trying to compare the classic computing and quantum computing by only using the time complexity, if we can do some cheat. For example, if we for the classic computing we will use only one computing resources, we can claim that the complexity is very high, like the order of n for this operation. However, this does not consider the parallelism at all. And if we only consider the parallelism, and we totally ignore the space complexity, we can, for the classic computing, we can obtain the time complexity as order of 1, but we need a lot of computing resources. So we believe a more fair way to do the comparison between the classic computing and the quantum computing is try to use the time and space complexity. And you can see for this example, if we use the time and space complexity, they have the same result. Both of the complexity will be order of n. So now the question is that for the quantum computing, what will be our time complexity, or also what will be our the space complexity, the resource complexity? And so for the time complexity, we will use a circuit length, because for each gate, actually it will use one step to complete such kind of operation. So we will use the circuit length as our time complexity. And also for the space, actually we will use the number of qubits, because it will also related to the parallelism can be integrated into such kind of quantum circuit. So when we consider the time and the space complexity, actually we will use the number of qubits to times the circuit length as our final result. So in this way, we build up a fair way to do the comparison between the classic computing and the quantum computing. And the next question is that whether we can obtain our goal, that is whether we can reduce the complexity for the classic computing, that is order of n for the new operation, to the order of polynomial log n in our quantum computing. And you can see, so for the left-hand graph, for this graph, actually it is a typical graph for the quantum learning system. We have the encoder to encode the feature into the quantum computer. We have the UW to embed our weights to the quantum computer. And finally, we have the measurement. And it is very easy for us to know the complexity of the third part. For the number of qubits, it will only need 1 qubit to host the result. And also the number of gates is related to the number of qubits. And one thing I want to mention here is that so for the n, it represents the number of input, because, and also for the qubit, actually it is possible for us to use log n qubit to encode all of these features. And therefore, the number of gates for Yong operation will be order of log n. And so in this case, for our input x and also weight w, actually the number of qubits will be order of log n. But the question here is that how many gates we will use to encode this stuff. So this will give us the answer whether we can achieve the quantum advantage against with the classic computing. And so what will be the goal of this tutorial, actually, of our research work? And the first goal is that we want to creatively implement the neural operation onto the quantum computer by using such kind of such kind of three-stage design. And the second goal is that we want to implement it in an efficient way so that we can reduce the complexity from the classic computing to our quantum computing. And the third goal is that we want to scale up the quantum system without involve a lot of measurements. So here will be the agenda for the second session. Actually, we will first introduce the data preparation and encoding, and then we will introduce the quantum circuit design. After that, we will try to introduce the challenge. How can we achieve the quantum advantage? So for the first step, what we do is that we go back to see the design of the neural network onto the classic computing platform. And we can see that when we try to map the neural to the classic computing platform, we will undergo the pre-processing to encode the data to the hardware like the FPGA. Then we will design the hardware accelerator. After that, we will have the post processing. And so in this way, actually, we can formulate such kind of three-step or three-stage design. We have the data pre-processing, we have the hardware acceleration, and then we have the data post-processing. And come back to the quantum circuit design, we believe we will also follow such kind of three-stage design. But when we design the quantum circuit part, actually we will further divide them into three sub-parts that include the UP part, that is the quantum state preparation. We encode the feature to the quantum circuit, and the UN part, that is the quantum neural computation, that is the main part, like the industry in our classic computing. And then we have the measurement so that we can read out our data from the quantum computing to the classic registers. And also on top of this, we will have the data preparation at the beginning and the data post-processing after the quantum circuit design. So in this tutorial, actually, we will follow such kind of 5 steps to introduce each step in details. And so for the first step, that is data preparation, and all stuff is about how can we encode the data to the quantum computers. And so for here, we want to ask the first question is that can we encode an arbitrary number into the quantum computer? And you can see here the answer is yes. So remember that actually for each qubit, actually we have different states. And if the initial state is known as a ground state, and it represents the 0. And if we apply the X gate, the X gate here, actually we can change the state of the ground state to the excited state. Therefore, we can represent 1. And if we interpret multiple qubits to represent one number, actually we can represent any numbers. So this is just a binary number, a sequence of number. For example, if we regard this number from bottom to top, actually that is 1100. So such kind of binary number where we can represent the number of 12. And if we regard there is a dot point, for example, at this place, actually it can represent the number of 1.5. Also, if the position of the pointer moved to the second place, actually we can have another number. But whether this approach is efficient, the answer here is that actually this operation, this design is not efficient at all, because in order to encode one number, actually we need k qubits, we need n qubits here. So we call such kind of design as a 1-to-n mapping. And now we are thinking about whether we can use a superposition introduced before to encode the data. And you can see for here, if we apply a RY gate with a parameter of pi over 3, actually we can change the qubits from the probability from 0 to 25%. So in this case, actually we can encode the data 0.5 in 1 qubit. And for this mapping, for this encoding, actually we are doing the 1-to-1 mapping, and this is also known as angle encoding. but it has some limitations, like the data need to be in the range of 0 and 1 because it is probability, right? So then we are in the range of 0 and 1. And also the complexity is order of 1 in the classic computing. We are moving forward. We are trying to see whether we can further leverage the entanglement to represent the data on the qubits. And we can see that in this way, in order instead of using 1 qubit to represent one number at one time, for this case, actually, we can use 2 qubits to represent multiple data. If you still remember, we introduced that if we have n qubits, actually, we can have 2 to the power of n states. So in this way, actually, if we have 2 qubits, actually we can represent these 4 numbers by using such kind of circuit design. And it also has some limitations, like the sum of the square of the data need to be 1. This is limited by the physics of the quantum computing, because the amplitude, the probability of each state should be, the summation of these states should be 1. And also, it may incur some high cost to encode the data. But from the number of qubits perspective, actually, in this case, we will encode n data onto log n qubits. And here we do some comparison. So for the 1 to n encoding, actually, for the left hand side here, for the comparison, we have the complexity on our classic computing. So if we want to encode n number to the quantum computers, actually the complexity will be order of Pn. And so for the data limitation, it has no data limitation, but and also the encoding complexity is no. And for the 1-to-1 mapping, the second method, actually we will use n qubit to encode n data. And the limitation of the data is that the value of the data should be in the range of 0 and +1. And also the encoding complexity is very low because we only need to use 1 gate to encode the data. And for our third encoding approach, actually we will do the n to the log n encoding, and the number of qubits can significantly reduce because we can encode n data onto the log n qubits. And also we have some data limitation, like the second one, that is because the summation of our amplitude should be 1. However, the encoding complexity may be high. I use the word maybe because actually people are still doing the research in this field. How can we encode the data onto the amplitude in an efficient way? So, but for this slide, what we can conclude is that unlike the first 2 encoding approach, actually we cannot reduce the number of qubits to the log n level. This is what we want, because if we want to achieve the quantum advantage, actually we need to reduce the complexity from order of n to the order of polynomial log n, right? So the n to log n encoding is the only way, is the only hope for us to achieve the quantum advantage. So in a quantum flow, we will first investigate the encoding approach by using this way, by using the amplitude encoding. And so for here, what we do in the quantum flow is that for the first step, we are doing some data preparation. So in this case, we are given the classic data, like the image data, 28 by 28 image data, and also the number of qubits to encode the data. For example, if we have only 4 qubits, as you know, if we apply the amplitude to encode the data, actually the complexity will, the state that we can represent will be 2 to the power of 4, and in this case we can represent 16 states. And so in this case, what we need to do the data preparation, actually, you know that we want to encode 28 by 28 images. So the first thing to encode the data to the 16 states is that we need to do some downsampling. And the second thing that we need to, because you know, for the quantum computing, we have some limitations on the representation of data, so that we need to convert the data so that it can be mapped to the state vector in by using a unitary matrix. So for this way, actually, for this visualization, we show that for the first step, we do the downsampling, and then we will convert the arbitrary data in our image data to a unitary matrix so that it can be encoded to the quantum computer. And in the second state, we will apply the created unitary matrix to the qubit, so then we can encode the data onto the quantum computer. So what you can see here is that because for our ground state, it is in the 0, state. So in this case, we have the initial state as 1, 0, 0, 0. And you can see for here for the data matrix, because after we generate the unitary matrix, all of the data, the information of the data will be calculated, will be collected in the first column. So when we apply such kind of data matrix and multiply the initial state, actually we can convert the initial state to the state that we expected on the quantum computer. So this is related to our real data. And so for the IBM Qiskit implementation, we can use the unitary gate to create such kind of unitary gate, and after that we can append the unitary gate onto the circuit, so that we can encode the data. So for here we have a hands-on tutorial. So if you open the code lab here, what we can see is that we can we provide the user the full code. How can we do the downsampling, do the normalization, and after that we can encode the data to the quantum circuit. And let's run the code here and see what we will obtain. So for here, we at the beginning we have the input image, that is a 6, and after that we do the downsampling. And so for here we have the quantum data to be in this way, and it is represented by the floating point. And after that, we will create our quantum gate to encode the data. And what you can observe here is that for such kind of 16 data, so this is the data we have we want to encode to the quantum circuit. So this is equivalent to this one. And after that, we apply the quantum gate to the quantum circuit, and we also can do the measurement, and we also can do the simulation to obtain the state vector. And for here, you can see that after we run the quantum circuit, actually we can see that, for example, for this data, it is successfully encoded to the state for the first state of our quantum computer. So in this case, actually we can, so by using this code, actually we can convert each data to the quantum circuit. Okay, if there is any questions from our audience, maybe you can just raise your hand, and then we can answer the question at this step. All right, if there is no questions, we will move on to the second part. So for the first part, we do the data preparation on the quantum circuit, and now we are thinking about how can we encode our weight to the quantum computer. And so for this task, for our third step, actually what we do is that we have a circuit with encoded input data X, and what we want to do is that we want to train a binary weight W for one neural computation. So for this W0 to Wn, and which will be associated with each data. And after that, we want to place some quantum gates on the qubits, so that we can perform the function that is similar with the neural computation in the classic computing. And then we will do some verification to see whether the output data of the quantum circuit will be exactly the same as the classic computer. So we will do such kind of task, and this is our target. We want to do the summation of our input data and the weights, and then we want to do the normalization. After that, we want to have a nonlinearity square function, a quadratic function here. So we have two assumptions. The first assumption is that all the parameters and weights are binary, so that is related to the binary neural network. And the second assumption is that the first weight will be always +1. So in this case, actually, if the first weight is not +1, actually we can use the negative weight to obtain the same answer, to obtain the same result. This is because the nonlinear function we applied is a quadratic function. So in this case, actually, we can further split the task into 3 steps to obtain our final result. And the first step is that we do the multiplication between our input data and our weights. And our second step is that we do the normalization. And after that, we will apply the quadratic function into our quantum circuit. And so for the first step, what we do is, and for example, if we have the last weight to be the -1, we want to do the multiplication between A3 and W3. So then we can obtain the middle data M3, that is the negative of A3. So if we transfer such kind of problem to the multiplication between the matrix and the vector, what we want to do is that we want to find a quantum circuit that can implement the unitary matrix like demonstrated here. So if we can find a quantum circuit that has the same function as this matrix, what we can do is that we will do the multiplication between the matrix and our input, and you can see that only the last element is -1. So then we will do the same computation as we expected. We will apply the -1 on our last amplitudes, and in the quantum circuit, actually, we if you still remember in our very beginning when we introduced the quantum gate, actually the control Z gate can exactly implement the same function. So the the matrix representation of control Z gate is exactly like the matrix we demonstrated here. And after that, what we are going to see is that how can we extend such kind of design to different for different weights. So if the weight is on the last position, in the last position, actually we can directly apply the control Z gate. If it is in the second position, actually we can apply the 2x gate. One is before the control X gate, and the other one is at the end of the control Z gate. So what we do is that actually at the very beginning we flip, we change the amplitude of the 0, 1 to 1, 1, and then we apply the control Z gate to flip the sign of the state 1, 1, and after that we flip the state back to the 0, 1. So in this case, actually, we can flip the sign of the 0, 1. That is equivalent to do the multiplication between -1 and and our input in the second position. And for the third position, we have the similar implementation. So in this way, actually, for every possible weights, actually, we can use the combination of this basic function block to implement these weights. And in our second step of design is that we want to do we want to accumulate all the data and then do the normalization. So what we want to do here is that we want to accumulate the intermediate data to be the amplitude of the first state, that is a 0, 0 state on the 0, 0 state. And what we do is that we need to find a matrix which has the normalization as a coefficient, and all of the element in the first row should be 1. If we can create such kind of quantum circuit to implement this function, actually we can complete our second step. And our design is to apply the 2 Hadamard gates to implement this thing, because if you still remember, the first row of Hadamard gate is always be 0, 1, and 1, and it has a coefficient that is the number of qubits that is related to the number of qubits. And if we apply the multiple Hadamard gate, we will do the tensor product, and the result of the tensor product will be the all of the elements in the first row should be 1. So this is exactly the same as our requirement, and the coefficient is comes from the coefficient of the Hadamard gate. So for each Hadamard gate, we have a square root of 2. So if we have n qubit, actually we can implement such kind of thing. So after that, at the end of the step, actually we want to incorporate the nonlinearity, that is the quadratic function, onto our results. And here we will what we do is that we first flip the amplitude from the 0, 0 state to the 1, 1, 0 state. And so for here, the last 0 will be our auxiliary amplitude, auxiliary qubits. And after that, what we do is that we apply the Cardiff gate, that is a control X gate. So this gate means that if and only if the first 2 qubit is in the state of 1, so that is in this state, actually we will apply the X gate on our third qubit, so that is on the last qubit, on this qubit. So for logically, actually what we do is that we swap the state, the amplitude of the state from 110 to 111. And if you can observe in our final obtained the quantum state, you can see that if the amplitude of the last qubit is 1, you can see that for the amplitude, only our last state has amplitude. All of this state has amplitude of 0. And after that, if we do the measurement, it will the probability of our the last qubit to be 1 will be the square of the amplitudes. So then, and also for this stuff, it should be 0. So then it will not affect the result. Only the last state will affect our results. So in this case, actually, we incorporate the quadratic into our quantum circuit. And we also have a tutorial on this part. And if we run the code, actually you can see that we can do the correct calculation. So you can see here we have a lot of functions, but you do not worry about this stuff, because at the end of the day we provide a library. We provide a library so that it integrate all of this function in the library, so that you do not need to worry to implement the details. You just need to call the very simple interface so that you can implement the quantum circuit. Okay, so let's just wait for a couple of minutes so that we can obtain the results. Okay, so you can see here for the first 2 steps, actually we prepare the data, and also this is our data preparation part. And so for here, we created the quantum circuit, followed our design introduced in the tutorial. And after that, so this is the result obtained in our quantum simulation. We implemented this quantum circuit and execute it, and finally we do the measurement on our last qubit. And you can see the result of the probability is 0.25. And so for this place, actually we do the simple implementation as a quantum as a neuron that we designed, so that we have the weights, we have our input data, we do the we flatten the data and multiply it with the weights, and also we do the quadratic function and do the normalization, and you can see this. So this is our you can regard this as a golden result, and this is quite near approaching to our simulation result. So there is some so the results are not exactly the same. This is because we can control the number of shorts. So if we increase the number of shorts on quantum computing, actually we can make our result to be more approaching to the real results. Okay, so this is our second part. How can we do the calculation of the for the quantum to implement the neurons? And the last part is that we want to apply the co-design philosophy to design the quantum circuit so that we can obtain some quantum advantage. So before we go into deeper, actually we will demonstrate, we will show some challenges exist in today's quantum computers. The first challenge is that we have already talked about this. For different gates, for different quantum gates, actually all the gates are linear operation. So how can we incorporate the nonlinearity into the quantum circuit? And we also show one possible solution is that we do the measurement for each layer, and after that we connect, we encode the data back to the quantum circuit. However, we will go through the quantum and the classical interface multiple times. And this operation itself is not for free. Therefore, well, actually also as pointed out by our work, actually such kind of state preparation can easily dominate the performance. And the third challenge is that how can we reduce the complexity to help us to obtain our ultimate goal. That is, we want to reduce the time complexity from order of n on the classical computing to the order of polynomial n on the quantum computing. And so we in the quantum flow, actually we provide such kind of co-design framework. We will not only consider the machine learning model to directly map it to the quantum circuit. We will also leverage the property of the quantum circuit to design the machine learning model. And also we will have a QF map to map the design to the quantum computer, to the quantum circuit, and to the finally physical qubits. And so this is an overview of all of the techniques we have already introduced. That is, we applied the design of quantum circuit to implement the binary neural network. And so for this, in this case, what we do for our input is that we apply the amplitude encoding to encode our input to the quantum circuit. And you know that at the end of such kind of circuit, we do the conversion from amplitude to the probability, so that we involve the quadratic function into the quantum circuit. And for now, if we want to, I mean, connect the multiple layers without do the measurement. So the task here is that we want to directly use the probability as the input of our second layer. So this will motivate us to go back to see the encoding of our input. So for the first for our previous design, we encode the exact value of this input as amplitude in this qubits. So for now, what we need is that we need the input to be interpreted as a probability. That should be the random variable. And if we can encode the neural network, so if its input is a random variable, and then if we apply such kind of quantum circuit design in at this position to, I mean, before the measurement, then actually we can connect multiple layers without going to the measurement. And also we involved the quadratic function in the whole process. So in such kind of thing, actually, what we do is that we propose another kind of encoding by using the angle encoding, so that we can encode the data from the classic computing to convert it to a random variable represented by the qubits. And we also followed the 5-step design to see, after we change the data encoding, how can we change the quantum neural computation so that we can do the same function as the neural in the classical way, in the mathematical way. So so for the encoding, it's very simple, because we only need to use RY gate to encode the data, so that we can guarantee the negative ones corresponding probability is exactly the same as our input data. And for the neural computation, if you still remember, we will do the multiplication between the input and the weights. And this step is also very simple, because for each qubit, it represents one data. And if we want to change the sign, actually, because so now the data is the random variable. So what we do is that we will change we will just apply the X gate, so that the probability will be swapped between -1 and +1. And after that, we need to do the neural computation. Actually, this is the most difficult part. As you can see in this slide, actually, we have a very detailed analysis so that we can have a general design for all kind of inputs. Actually, we can use this kind of weight encoding so that we can encode the weight to the quantum circuit. And finally, if we apply the above proposed two types of design, we can connect all of the neural together so that we can obtain a quantum neural network. And as you can see here, at the end of the quantum circuit, we have one qubit indicate the probability of 3, and another qubit indicate the probability of 6. And we also provide an end-to-end implementation on the code lab. And by the way, if you just come into the to our tutorial, you can use this link to obtain all of the slides. And in the slides, you can obtain the link to the GitHub of the code lab or the code lab. And if you do not have the access to the Google, actually you can use the GitHub to deploy the code onto your own computer and run the code. So now let's go back to see our our third tutorial on-hand tutorial. So for here, we followed our design to design two layers. The first layer using our amplitude encoding, and the second layer using the angle encoding. And finally, let's just wait for a couple of minutes so that we can complete this part. We will also, like the previous way, actually, we will also pre-process our minister data and encode the data to the quantum circuit. And after that, we applied our previous design to implement the circuit. So let's just wait for it to install the package and run the code. I think maybe we are stuck here. It is still install the package, but okay, we can simply go through the code a little bit. So in the implementation, actually we have two set of weights. So this weights are for the first layer, and these two weights are for the second layer. And when we try to create the quantum circuit, actually we will implement the quantum register, that is a qubit for different part, and then we will apply the quantum circuit to implement the function. Okay, so we are moving on. All right, so maybe we can just let it run here, and we can move to the next part. How can we optimize the quantum neural? And so this is related to how can we find how can we design the quantum circuit so that we can squeeze the quantum circuit to the order of log n. And so for by using our previous design, if we want to embed one negative weight to the quantum circuit, actually we will use one quantum gate as demonstrated in the demonstrated here. So for this gate, it will change the quantum state 00001. So it will change the sign of this state. So in the worst case, there are half of weights that will be the -1. So and you know that if we consider the complexity of this implementation will be at least order of n. So we cannot achieve our goal to reduce the complexity to the order of log n. And a better design is proposed by the author Tachino in the quantum information. And from this paper, actually they use the Z-gate to change a group of sign so that it can leverage some parallelism in the quantum circuit. But even in this way, actually authors in that paper demonstrated that the complexity of the full quantum circuit will still be order of n. And in our quantum flow design, actually, we have the observation that the weight order is not necessary to be fixed, and it can be changed along with the change of the input order. And the benefit here is that in this case, there is no need to require the position of sign flip to be exactly the same with the weights. Instead, actually, we only need the number of signs to be the same. And so for here, we demonstrate that for the previous task, if we want to flip 6 sign, actually for here we only need 2 quantum gate to implement this function. And based on this observation, we propose a recursive function to design the quantum circuit for any arbitrary given weights. And we can see here that in the worst case, all of this CZ gate will be applied. And if we explain the control Z gate to the basic gate, actually the complexity will still be order of log n squared. In this case, actually, we have successfully reduced the complexity of our computation from order of n to the order of log n squared. And we also have the detailed implementation in the code name. I'm not very sure whether the previous run has already been completed. Okay, so for the so for here actually we also have the implementation, and now let's go back to see the previous tutorial, hands-on tutorial, and you can see after we do the downsampling and the encoding, what we have is that so for here, what you can see is that for this number, that is the measurement result of our first qubit, and so for this number, that is the measurement of the second qubit in our quantum circuit, and so our prediction class will be 1, and that is exactly the same with the target class. So you can see that our input will be 6. Actually, we have 2 inputs from the MINISQ data. That is 1 is 3, that is associated with the label of 0, and 6 is associated with the label 1. So in this case, you can see that we do the correct prediction by using the quantum circuit designed in our example. And so for this one, actually we replace the UN component by using the optimized UN. And if you have interest, you can find the code in the code lab, and then you can run it. So for here, I will not go through detail of this hands-on tutorial. And finally, I want to report the result obtained by the QuantumFlow. And you can see here, for this graph, actually the x-axis represents the number of neurons. That is the size of neural computation, and the y-axis represents the cost. And the red line and the red dots represent the result obtained by our designed proposed quantum flow, and the black line represents the cost for the classic computing, and the blue line represents the existing design which is introduced in this paper. And you can see for the number in the box, it represents the gap between the classic cost, the cost of the classic design and our proposed quantum flow design. As you can see, along with the increasing of the input size, actually the gap between the classic design and our quantum flow will consistently enlarged. And you can see when the size reaches to 2000, actually the improvement on the cost will be 64 between the quantum flow and the classic computing. And we also applied it to the MINISQ data set, different MINISQ data set, and you can see that the proposed design can obtain more than 10 times reduction on the total cost. And finally, we also demonstrated that in our quantum flow, we have another component that is known as batch normalization. And you can see if we apply this technique, actually we can maintain the accuracy of our proposed quantum design to over 90% for the accuracy. And finally, this is also a very interesting result obtained by our quantum flow. And so we are trying to complete the classification task demonstrated in the figure A, and figure B is our structure of the neural network, and the figure C is our quantum circuit design. And now we want to map the quantum circuit to the real quantum computers. And the figure D represents the IBM quantum one of the IBM quantum processor with 5 qubits, and the different color represents the error rate. And now the interesting observation here is that for figure G, actually we applied the default mapping method to map the logical quantum circuit in the figure C to the physical qubit in figure D, and we can see that so this is our golden result. And F is our simulation result. So for the simulation, actually, we can obtain almost exactly the same result as the golden result. So the accuracy for this one is 98%. And there are 2 positions. We have some errors, error prediction. This is because actually, because our quantum simulation is based on the has some randomness, so that it is some probability that it cannot predict as exactly the same. And so for figure G, actually this figure G and figure H, actually both results report our result after we run the quantum circuit on the real quantum computers. And the figure G, we do not do the optimization for the mapping, and it applied the default mapping. And you can see there are a lot of points actually we do a wrong prediction. And the figure H, we do the error-aware mapping. So we consider we want to map the quantum qubit with the most least gate onto the qubit with the highest error. And in this way, we can observe that actually we can resume the accuracy to an acceptable level. So in this case, there are more prediction are correct compared with figure G. So this indicates that when we do the design of the quantum machine learning system, we indeed need to consider the error into our design process. And also this driven our second and third talk, we want to minimize the effect of error in our quantum machine learning system. And so for here, we also have provide a hands-on tutorial to obtain our result in the paper. And I think this will be the end of this session. If you have any questions, feel free to ask. I think we can have a couple of minutes for the Q&A. Is there any question from the audience? Okay, if there is no questions, maybe I think we can move to our third session. So Zhepeng, are you here?
Hi, Dr. Jiang, I'm here. Yeah, I'm here.
Okay, great. So maybe you can try start to share your screen, and then we can switch to the third session.
Okay. With me for a minute.
Sure.
Can you see my screen?
Oh yes, actually I can see your screen. Okay, so let me introduce. So the third session will be the talk will be given by Zhepeng Wang, who is a PhD student of in my group, and the topic will be the quantum neural network comparison. I think this will be the very first work to involve the comparison idea to the quantum neural network. And here we'll show you the detail of our design, and also I think the hands-on examples. And so Zhepeng, maybe you can start.
Oh, okay. Yes. Okay, yeah. So, hello everyone. I'm Zhepeng Wang from George Mason University. Today, I would like to introduce our work on the compression of quantum neural network, which has been accepted by and will be published by this year's ICCAD. So firstly, let me briefly review the concept of compression in classical machine learning, which includes pruning and quantization. As you can see in Figure A, this is classical neural network without any compression. So the weights of this neural network could be arbitrary real value, and then we can prune the and then we can prune the value which is close to 0. As you can see in Figure B, this is the output after we apply pruning to the original classical neural networks. These three layers for these three ways, their value are close to 0, so we prune them, and also the related neural will be pruned as well. So after the pruning, we can also apply the quantization to the pruned neural network, which means we will quantize the value of the weight to some fixed value level. And for this quantized value, we can simplify their representation on the hardware, for example, in FPGA. And through the compression, we can save the space for the machine learning model and also accelerate their computation. So what does pruning and quantization look like in quantum machine learning? Figure E shows a quantum machine learning model implemented as variational quantum circuit in quantum devices, where the quantum gates have trainable parameters, which is the rotation angles of the rotation gate. Then then we can prune these three rotation gates because the rotation angles are close to 0 or 2 pi. After pruning, we can apply the quantization. As you can see in figure G, all of the value of the rotation angle are some fixed level of angles. Yeah. But why do we want to apply pruning and quantization on quantum machine learning model? It is because that we want to reduce the circuit depth of the physical quantum circuits, and the short circuits has benefits like mitigating noise effect of the current quantum computers and speeding up the execution on the quantum computers. By comparing the pruning and quantization in classical machine learning and quantum machine learning, we can find two major differences, which we listed here. And for pruning, in quantum machine learning, we will not only prune the zero value, but we will also prune the value like 2 pi, 4 pi, etc. And for quantization, different quantization level may have different cost. And these 2 points can be illustrated with these 2 figures. As you can see, the figure in the top shows the compression on classical neural network. As you can see, only the value only the value 0 will be pruned. And for the quantization, the cost of the operation is the same in terms of the clock cycles. But for the compression in quantum machine learning, we will not only prune 0, but also 2 pi, 4 pi here. And for the other fixed level of quantization, the compression cost is different in terms of the circuit length. And in this slide, we show an example of quantum circuit before and after compilation. As you can see, in before compilation, there are 3 logical gates. And after the compilation, these 3 gates will be decomposed to the basis gates through the Qiang compiler. No, through the compilation, not just the Qiang compiler. Yeah, and for these and as you can see, for each gate, they are decomposed to the sub-circuit with different lengths. And this table is an example summarizing the depths of different gates through the Qiang compiler. As you can see, when the type of gates or the value of the rotation is different, the circuit depth after the compilation will be different. And it is also expected that when we compile the circuit with different settings, such as different basis gates, the table should be different. Therefore, we claim that quantum neural network compression should be compilation a while. Based on the observation I just mentioned before, we proposed QuantumFlow+VACSEN, a framework to compress quantum neural network implemented as variational quantum circuit. And there are 3 steps to go through to run the QNN model on quantum computers with the QuantumFlow+VACSEN. The first step is preparation, and the second step is compression, and the last step is deployment. So now let's go to the details of each stages. Firstly, we should take a look at the stage 1, preparation. Yeah, in stage 1, we need to prepare the required input to the stage 2, the compression. More specifically, we first need to build a compression level lookup table, and the input to build such kind of lookup table should include information from quantum backend, where the basis gate is the most important information. And also we need information from the compiler. And the users can also specify whether we want to enable pruning or whether we want to enable quantization. Besides, we need to pre-train a quantum neural network for the compression. In this slide, we want to emphasize that compression level is a combination of pruning and quantization, which is clearly shown in this figure, where you can see that the green part corresponding to the pruning level and the blue part corresponding to the quantization level. And as we mentioned before, for pruning, not only 0 angle can be pruned, but also angles like 2 pi, 4 pi can be pruned. And for quantization, different quantization level may have different cost. Besides, for the variational quantum circuit pre-training, we want to highlight that the training process is implemented with Touch Quantum, an open source library for the efficient training of quantum neural network. So now let's go to the hands-on session for this step. For running the in this session of the tutorial, we prepared 3 hands-on tutorial. But for running the corresponding codes, we will leave them after I introduce all of the technical details of the framework. So to build up the lookup table, as you can see, the input is the fixing point list. As you can see here, the list where the value is like the pi divided by 4 or the pi divided by 2. Yeah, and also we need to prepare the logical gates to be used. Here we prepare 6 logical gates for the lookup table, and also we need to specify the quantum backend. To construct the lookup table, we provide the API, the LUT construction, and this function will take this input as the parameters, and it will compile the logical gates with the parameter specifies and get the output the compression level lookup table, which is shown here. As you can see, for example, for the third row, when the rotation angle is pi, for Rx gate, the corresponding depth after compilation is 1, and for Ry it is 2. So after we finish the step 1, we will come to the second stage, the compression. And the first step to do the compression is to reconstruct the lookup table for the ADMM, the alternating direction method of multiple layers. Before we do the reconstruction, we want to formally define the compilation aware QN compression problem. As you can see, given a variational quantum circuit with trainable weight theta, the lookup table T, and a quantum compilation C, the problem is to determine the trainable parameters such that we can minify the object function listed here. As you can see, there are 2 terms in this objective, which is, well, the first term is the training loss on the given training set, and the second term is the TCD theta, the circuit depth of the variational quantum circuits. And for the constraints, we need to constrain our each trainable weight to the value in the lookup table, which we got from step 1. And in our framework, we choose ADMM to solve the optimization problem we just formulated. But before we apply this optimization method, we want to reduce the search space for ADMM, which is the motivation for us to reconstruct the lookup table. More specifically, in the reconstruct lookup table, each row corresponds to each quantum gates existing in the variational quantum circuit. But instead of having multiple choice of the compression level, which is listed in the previous lookup table, now we only has 1 target compression level, and only this compression level will be used for the ADMM. And then therefore, the whole process is conducted by traversing all of the quantum gates in the variational quantum circuit and select the compression target with the highest metric. And for the metric, we in our paper we provide a heuristic metric, looks like this, which is shown in this formula. As you can see, this is a product of 2 terms, where the first term is the accuracy, where the totem is accuracy of the variational quantum circuit under the new quantized or compressed values, and the TCD theta is the inverse of the compression ratio by changing the parameters from theta to fix the compression level. So now we came to our second hands-on session. In this part we want to reconstruct the lookup table for ADMM, and the input for this step is a trained variational quantum circuit, and also the original lookup table we obtained from the first step, and also the matrix function we define, which consists in the term of accuracy and the length of the compilation. For each parameters in the variational quantum circuit, we will replace it with points at the compression level in the original lookup table, while fixing other parameters, and then we will calculate the metrics of each new model. Finally, we will select the point, the value with the highest matrix as the compression level for the ADMM. And as you can see, for the reconstruction, we provide an API, which is lookup table LUT reconstruction, and the output is the new lookup table for the ADM, which as you can see, which entry corresponding to a quantum gate in the variational quantum circuit, and the value is the target compression level. So after we reconstruct the lookup table, we can now compress the quantum neural network with ADMM. In this step, we relax the constraint in the original optimization problem, which means that not all of the parameters will be compressed. But so in this way, we will only compress some insensitive values in the variational quantum circuit, and in this way we can maintain the higher accuracy of the original model. So more specifically, each parameters can either be compressed to the target value in the reconstructed lookup table, or we just not compress them. And after the compression, to recover the accuracy, we will retrain the model while fixing the parameters in the compressed case. And this slide shows more details about the ADMM for QN compression. So if you and so due to the limitation of time, I will not go to the technical details of this optimization problem. But if you are interested in the whole process, you can refer to our paper, which has been submitted on arXiv. So now we will go to our third hands-on session for the compression based on the ADMM. The input here is a trained model and the new lookup table we got for the ADMM. And in this part, we will compress the model with ADMM and also fine-tune or retraining the compressed model. So finally, the output we got the output is the compressed model, and this table shows the information about the model before compression and after compression. As you can see, the circuit length is significantly reduced, and also the accuracy is even improved. And these two figures shows the quantum circuit before compression and after compression. And the red in the bottom figure, the gate with red circle indicates the gates we applied with pruning, and the gates with blue circle indicates the gates with quantization. And after the compression, finally, we will deploy the compiled variational quantum circuit onto the quantum computers for execution. And due to the time of limit, we do not arrange a hands-on session for the deployment. So now we have go through all of the 3 stages of CompVQC. And this this figure summarize all of the summarize the overview of this framework. So now I think we can run the code on the Colab to do our hands-on session. So I will open the Colab first and share my screen. So okay, as you can see here, this is the Colab for the hands-on session of this part. So for the first part, we build the lookup table. This code is just for the setup, and then after the setup, here is we define the API to construct the lookup table, and then we will test the function of this API. As you can see here, after we print out the output, we got a lookup table for the different compression level of different logical gates, and then we will reconstruct the lookup table. So this part is just for setup, and we will generate the data set for the evaluation. Then we define the model to be pre-trained. So here, this is the test function just on the data set. And this is the function used for the lookup table reconstruction. Finally, we will prepare our input and also run the API lookup LUT reconstruction. And as you can see, this is the output. This is the reconstructed lookup table for the compression. So in the third part, we will do the training and the compression. So here we define the classes for the ADMM optimization. And this is the function for the ADMM training and the test. Here we prepare the input for the ADMM training. And here we print out the quantum circuit before the compression. And as you can see, the circuit length is 51 and the accuracy is 94.2. Then we will apply the ADMM optimization. And after the compression, we will do the retraining to recover the accuracy of the model. As you can see here, the circuit length after the compression is 35, which is significantly reduced than the previous value of 51, and also the accuracy is improved to 97. Okay, so now I will switch back to the slides. Okay, so after the hands-on session and the introduction of the framework, we finally want to take a look at some experimental results. And this slide first shows the simulation results on the machine learning dataset. And we compiled our conf-VQC with 4 baselines, which is the vanilla VQC without any compression, and the pruning, which only pruning the value close to 0, and the conf-VQC with pruning only, and the conf-VQC with quantization only. And in this table, we can conclude that our proposed framework can maintain the high accuracy with less than 1% accuracy loss, and the reduction of the circuit length is up to 2.5 times. Oops. And the figure on the bottom show that the QuantumFlow could push forward the parental optimal in terms of the circuit depth and the accuracy. And the right figure shows the experiments on datasets with increasing classes. We can see that under all of the settings, QuantumFlow could achieve higher accuracy with shorter circuit than the other compression baseline. And we also evaluate the QuantumFlow on multiple real quantum circuit. And more specifically, we evaluate on IBM quantum computers with the synthetic datasets. And as you can see from this table, we can conclude that the QuantumFlow can reduce the circuit length by 2 times, while the accuracy is also higher in the noisy environment of quantum computers. So we can conclude that the circuit compression can make the quantum neural net model more robust to the noise. So after the introduction of our compression for the quantum neural network, I also want to briefly introduce the API of the QuantumFlow. And as you can see, we provide the open source library of QuantumFlow, and if you can just easily use it by import the QFNN to your Python code. And this slide shows the documentation link for the QuantumFlow API, and also this is the GitHub link for the open source code. And this slide just is a simple example to show the use of the API in QFNN. As you can see here, we given the number of input neurons and the number of the output neurons, the input data J, and also the weight of the quantum neural network, and also an empty quantum circuit. And then we will encode the input to the circuit. As you can see, we use the function like the add input qubits, the add oncs, and the add output qubits here. So, and after we embed all of these input, we will do the forward for the U layer, which is also defined in the library. And the output is the circuit with M output qubits. And here, this code will print out the circuit. And so here we also provide hands-on session for this code. So I will open my Colab. Okay. Show my screen again. So you can see, this is the hands-on session for using the QFNN library. So you can see here we import the many APIs from the QFNN, and then we will prepare the data for the inference, and also load the pre-trained model, and build the QFP layer, PNet, using the API provided by QFN. As you can see, the U layer circuit is the model defined in QFNN. And then finally, as you can see, we print out the circuit for the QFHNet, which is introduced by Dr. Jiang in the private session. And also, this is the one after the compilation, and we can use the model to do the simulation and compile. Okay, so here for the results. Okay, so for the results, maybe at the end. Okay, so it looks like that the result is flashed by the warning message, but our point here is that we want to show that the results in the quantum simulation is the same with the one, but if we only run the QFN on the classical computers. As you can see, the results should be the same in this cell and also in this cell. Okay, so that's all I want to present today. So any questions? Okay, so if there are no questions, I will end my part.
Sure. Actually, I think we can have a 10 minutes break, and after that, because you know that we have already consequently have the talk for more than 2 hours. So let's just have a 10 minutes break, and then we will come back on 10:45, and so that we will continue for our fourth part of the presentation. Okay. Hi, all online helper. Are you here? I mean, the staff is the ES week staff. Suzhou, are you here? Actually, I think that we need to make a Dr. Professor Wang Yong as a co-host so that he can share the slides.
Yes, Weiwen. I think the volunteer has already added me as the co-host.
Okay, great.
Great.
So maybe do you want to share your screen? I can stop sharing my screen.
Yes, let me have a try.
Sure.
Yeah, Weiwen, could you see my desktop?
Yeah, I can see the empty desktop.
Okay, great. Let me try to share my screen.
Great. Actually, we can see the screen.
Okay, great. I'm ready.
Great. So I want that I am on site so that I can call people back to the to the station. I think we just because have a break, so maybe we can make some noises. They are no, we are continue so that they will come back. Anyway, I think maybe we can start it. And so our last session will be we'll be talk about the visualization approach to for the noise aware in quantum computing, and the speaker will be Professor Wang Yong from who is a tenure track assistant professor at the School of Computing and Information Systems at the Singapore Management University. His major research interests include the data visualization, video analytic, human-computer interaction, and also explainable artificial intelligence. His research goal is to develop a cutting-edge information visualization technique and interactive video analytic system to facilitate big data exploration and analytics. His research has been applied in different domains, including network analysis, online learning, smart factories, and also the fintech and the public speaking training. And a part of his research has been covered by media, including the NHKTV, IEEE Spectrum, and also ACM SyncGraph blog. So let's welcome Dr. Wang to give us a talk on the visualization for the quantum computing. So maybe this you can handle this.
Okay, sure. Let me adjust my Zoom a little bit. Okay. Okay, so all right. So Wang, can you hear me?
Yes, we can. I can hear you. By the way, maybe the host do maybe if you can, maybe you can resume the recording. We are okay. I see the recording is still on. Okay, so you can start. No problem.
Okay, all right. So hello everyone, and I'm Wang from Singapore Management University, and thanks for Weiwen's nice introduction. So like what we had just mentioned, actually, I'm currently working as an assistant professor in Singapore Management University in the School of Computing and Information System. So my research is mainly about data visualization. Yeah, so I obtained my PhD degree from Hong Kong University of Science and Technology in 2018. And after that, I stayed there for 2 years to work as a postdoc. And I joined my current university from 2020. Yeah, so today I'm going to introduce our latest work, VACSEN visualization approach for noise awareness in quantum computing. So this is actually a joint research work with like my PhD student Shaolun, and also 3 excellent collaborators like Weiwen and Ying and Qiang. So like I just mentioned, actually my research is mainly about data visualization, but you can see here actually Weiwen is a superstar or definitely professional expert in quantum computing, and also Ying and Qiang. So so you know, about maybe 1 year or almost 1.5 years ago, okay, we just have a quick chart and see, okay, hey, women just say, okay, you know, we have some issues about how to visualize and explore the noise in quantum computing. So Yong, could you help us with that? So you know, visualization is my expertise, right? So we think actually after a period of exploration, we found this is a really exciting research direction. And my PhD student Shaolun is also very excited about it. So that's how the whole story started. And for today's tutorial, okay, me and also my student Shaolun, we will go through the whole work. So maybe Shaolun, could you unmute yourself and do a brief self-introduction to all the audience? Shaolun.
Okay, Prof. Can you hear me?
Yes, go ahead. Just
okay.
A brief introduction.
Okay. So hello everyone. My name is Shaolun Ruan. I'm a PhD student at Singapore Management University, and I'm also the first author of this paper. And my supervisor is Prof. Wang, and my research interest includes the data visualization, human-computer interaction, and also quantum computing. So I think my goal is to you know, the quantum computing is very complex to understand, especially for the general public and the quantum computing novice. So my goal is to enhance the transparency and the interpretability of the quantum computing and makes it more easy to understand for the general public. Yeah. And next, the Prof. Wang will introduce the details of the design and the implementation of our visualization system. And then I will also introduce our evaluation part of this work. Okay, so Prof, you can go ahead.
Okay, yeah, thanks, Shaolun. Yeah, so this will be the basic agenda of today's tutorial about our work VACSEN. So I will briefly introduce background, motivation approach, and then I'll ask Shaolun. I'll hand over to Shaolun to go through a demo and ask our audience to participate in some hands-on practices. Okay, so first, for the overall background, I think as we already know, actually, quantum computing has been proved a considerable speed up our classic computing in recent years. So, like Google has demonstrated that this kind of quantum supremacy, they have been using this kind of like about 53 qubit quantum computer, and it can spend like 200 seconds to compute a random sampling task. That would cost about 10,000 years on the largest classic computers. So this is also what we call the quantum advantage or quantum supremacy. So due to this kind of significant advantage of classic computers, quantum computing and also quantum computers has become a very important and very hot research topic. So here are some basic knowledge about quantum computing. So the basic unit of quantum information in quantum computing is a qubit, which we can also call it quantum bit. So for classic computing, a bit always has two deterministic states, that is 0 and 1, which is a balanced state. Well, for quantum computing, there are two normal basis states for a qubit, which we can call it like status 0 and status 1. So the actual quantum state of a qubit can be represented by a linear combination of the two basis states, which is also what we call superposition. Well, the weights alpha and beta are actually complex numbers subject to this expression. Basically, the square sign of them will be equal to 1. And also multiple qubits can be entangled into to support the qubit induction, which is also what we call quantum entanglement. And the entanglement state of two qubits can be made while gate on the counter bit. So which can be like this kind of signal gate, so on and so forth. Okay, so we have actually different quantum computers. I think one of the most popular quantum computing platform is IBM Quantum Cloud Platform. So in IBM Quantum Cloud Platform, they have also provided different quantum computers, and different quantum computers actually have different quantum topology. And the transpiled physics circuit can be different according to the topology of this kind of qubit. So here are just some several representative examples, representative quantum computers from IBM quantum machine. Well, an important issue of this kind of quantum computing is the quantum noise. So quantum noise issue actually becomes, severe due to the variation of the topology of physical qubits. So basically, for different quantum algorithms, they are synthesized as quantum circuits, which we can also call them like logic circuits. And this kind of quantum circuits will be finally deployed to the quantum computers and be transpiled into physics circuits during the execution. Usually, we will, for specific quantum computing algorithm, we will go through the process of mapping the logic circuits to physical qubits to obtain the physical quantum circuits. And then the physical circuits or the compiled circuits will be specified to the actual quantum computers, so on and so forth. So even for the same quantum algorithm, the effects of the quantum noise on the algorithm can be significantly different. So here we have pointed out, the noise actually is a significant issue in quantum computing, but it is actually difficult to analyze the noise hidden in quantum computers. There are several reasons. First, there are a lot of this kind of like quantum computers. And also a lot of, we already have several different quantum computing platforms like IBM, Google, so on and so forth. And even for one quantum computing platform like IBM, they have provided different quantum computers. And second, even within each quantum computer, the number of qubits of can be different. And third, the calibration data. Here we have listed the potential calibration data, including like the qubit error and the gate error can be quite different, and also they are dynamically changing over time. So here we have listed 3 types of the widely seen physical calibration data, like T1 and T2, and also readout error and the gate error. Basically here we point out the CNOT error. So T1, T2, basically the errors they are corresponding to the time that the qubit hold the superposition state, and the time the qubit is not affected by the environment. And readout error, basically it means error that can affect the qubit state at the final reading phrases. So in this project, we basically just summarize the T1, T2, and the readout error as a qubit error, and the CNOT or gate error as a gate error. So that we can better group this kind of calibration data. Thus, is actually, so it's quite important to inform the quantum computing users or researchers, or it's important to make them aware of the noises in quantum computing. However, there exist many challenges that many come from 2 perspectives. The first perspective is, the compiled circuits can be varies even based on the same logic circuit. So basically the performance of the computers, like what I've just mentioned, the performance of the quantum computers rely on multiple factors of qubits and the quantum gates, like what I just mentioned, like T1, T2 readout error, so on and so forth. And these factors are actually dynamically changing over time, and it is challenging to visualize these complex factors as well as qubit topologic connections along a timeline. And secondly, a quantum algorithm can be compiled or transpiled to various compiled circuits with significantly different noise, even on the same quantum computer. For a large-scale quantum algorithm, this kind of compiled circuits can be like several hundred, according to Breuer's research. The noise of the compiled physics circuits needs to be evaluated from different perspectives. For example, like the circuit depths in the noise of involved qubits and the quantum gates. So here we have shown a figure. This is actually one of the screenshots from our system. It shows like several transpiled physics circuit of the same logic circuit. So you can see actually even for the same logic circuit, if we do different combination or transpilation, the resulted physics circuit can be different, and their performance can be different. So for the general quantum computing workflow, usually you will follow the 3 steps. Of course, the first step is, we need to implement the quantum circuit or the quantum algorithm by using some existing tools like a QuantumFlow. And then this kind of quantum circuit will be, after that, we need to select which quantum computer should be used to compile and to run our quantum algorithm or quantum circuits. And after select the quantum computer, then the next step is that we need to, actually we will not do that. The quantum computer platform will transpile the logic circuit or quantum computing algorithm into physics circuit. So these are our steps. Well, for this, the second and the third step, actually, for example, if you select different quantum computers, the noise can be different. For the qubit mapping and execution, different mapping and different execution, the noise will be different. So this is why in this in our project we are focusing on the second and last steps to visualize the noises and info users of the potential of the possible noises in those 2 steps. Well, according to our according to our exploration in the past few months, so we find actually there are no existing tools to reflect this kind of hidden noise in quantum computing workflow. And the most common practice is to just try the users will quantum computing research will just try to obtain less noisy execution results by just try and error. This is actually it highly depends on the user's domain knowledge, and it's kind of like time consuming because you need to try and see what is our array, our errors, and so forth. And usually, okay, you will take a long queuing time, for example, up to hours. So when you try to check what is our error of this kind of selection, actually it will take a lot of time. So it's not that convenient for the general quantum computing users or researchers to explore, to understand the underlying noises in the quantum computing workflow. So to fill this research gap, actually, we have followed a user-centered design process by working closely with 5 domain experts in quantum computing for over 5 months. So here are some basic information of the 5 experts or expert users in quantum computing. Their basic profile. Basically, we have one of the expert is from Northwest National Lab, and 3 of them are experts from different universities, and the last one is a PhD student majoring in quantum computing. And they also have slightly different research interests and research directions. So for this project, actually, we collected calibration data of different quantum computers. More specifically, actually, in this project, we just use IBM Quantum Cloud Platform as an example to demonstrate or to show the effectiveness of our approach. So here we have collected calibration data, including relaxation time T1 and defracing time T2, and also qubit radar error. Like I just mentioned, these 3 metrics we group them together as qubit error and also get error rate. We have collected this kind of calibration data, and also we have collected the real instructions. The compared physical circuits basically corresponds to the real instruction output from the physical circuit. It will basically specify the detailed usage of each qubit and each quantum gate in the transpiled physical circuit. So after we working together with domain experts for 5 months, actually, we summarize the detailed design requirements. So this kind of design requirements can be categorized into 3 aspects. So basically, also follow our quantum computing workflow. So the first aspect is about the quantum computer selection, because after you specify the logic circuit or basically the quantum algorithm, you need to select which quantum computer should be used. For example, if you use IBM Quantum Platform, you need to select whether you are using Jakarta or using some other quantum computers. And different quantum computers have different number of qubits, right? And also have different topologic structure. And the second part is about, you need to you need to pay attention to the compared circuit selection. For example, after you select a specific quantum computer, for the same logic circuit, they may be transpiled into different physical circuit. And finally, we also talked about the detailed requirements regarding user interaction. So for quantum computer selector, basically the requirement can be summarized to 2 aspects. Basically, we need to facilitate the temporal analysis of various noises of different quantum computers. And also we need to make users aware of the latest noise. So the historic noise is useful, but the latest noise also is relatively more important. Well, for the compared circuit selection, we need to provide users with an overview of all the compared circuits and its corresponding noise. And also sometimes we need to compare different physics circuit. We need to select which physics circuit is better, right? So we need to enable detailed comparison of the usage of the qubits and the gates and its detailed like noises, so on and so forth. And also we need to support real-time compilation and the fidelity validation. While for user interaction, basically we need to provide users with flexible interaction and intuitive visual designs. So inspired or informed by these design requirements, we propose VACSEN, a visualization approach for noise overlays in quantum computing. So VACSEN can info quantum computing users or research of the noise in quantum computers and the compared physics circuits. The automatic goal is that we can achieve a better execution result with high fidelity, high or better performance. So our approach basically consists of 3 major modules. So here, like I just mentioned, we take IBM IBM Cloud Computing Platform as an example. Okay, so we have for our system we have 3 modules: storage, data processing, and also visualization module. So store basically will store all the necessary data and processing. We need to do some basic processing of the region data like data cleaning, data formatting, calculating the corresponding noise values, so on and so forth. And we have proposed 3 major visualization views to help to info users of the underlying noises at different level, like quantum computing level and physical circuit level, so on and so forth, and the final outputs. So here is a brief overview of our system. So the user interface basically consists of 3 major visualization views. So the first part A, corresponds to the computer evolution view. It announces the assessment for all quantum computers based on the temporal analysis of multiple performance metrics. Well, this part basically, you can see here we have we're using IBM quantum computing platform. They have different quantum computers like Lagers, Pers, Yakatar, Linmar, Malila, so on and so forth. They're using this kind of lens to land their quantum computers. And here we propose this very intuitive and straightforward visualization to info users about of the overall noise evolution and also the detailed qubit status, detailed gate status. So in the subsequent slides, I will briefly introduce our visualization design. Later, I will hand over to Shaolun. He will show some online demos so that you guys can see more detail of how this kind of tool can be useful to improve the noise awareness in quantum computing. So this is a computer evolution view, and this part, after you select, for example, you select this quantum computer, then in this part we will visualize all the compared circuits. So this one is called this view is called circuit filtering view. It will support the filtering for the potential optimal compared circuits. And then for the part C, it is called circuit comparison. It will support the in-depth comparison regarding the performance of the qubits or quantum gates and the corresponding usage. And this, on the rightmost part, there are sub-views, which is just functional views. Like here, it's what we call control panel. You can configure different settings. And here it's a fidelity comparison. You can compare the fidelity of the compared circuits. And here this is what we call a probability distribution view. It visualizes the result of different state distribution of quantum circuits. So let me start from the first view, computer evolution view. Its automatic goal is to visualize, for example, the overall noise status of different quantum computers. You will visualize the noise status of the qubits and also the gates. So before I introduce the detailed visualization of all designs. So let me just show you some new designs or some alternative designs we have explored during the whole process. So here are some alternative designs we have explored, but we finally find they cannot be applied here. They cannot achieve our design goal. So for example, for this part, for part 2, this is initial design that is actually a general design for temporal analysis. However, you can see basically our idea is we can use like this kind of line chart to visualize the quantum, the qubit status or qubit errors, but it is not appropriate to visualize a number of qubits noise trains simultaneously in a Lyra space, and also it's difficult for us to identify the topology structure or the gate the topologic connections between different qubits. And also for the other 3 alternative designs, they suffer from different issues. So due to limited time, I will just skip this part. So let me introduce the details of our visualization design here. So for this visualization design, quantum computer evolution view, the core design is what we call circuit-like design. So, it's actually quite challenging for us to visualize the complex noise factors as well as the qubit topologic connections along a timeline or their temporal evolution. So this is our visualization design. The basic idea is, so here, we will use each row to represent the status of each qubit, and the corresponding error rate or the corresponding matrix of each qubit will be visualized by this kind of circle. So here we are using the circle radius to represent the metric, and also we're using the color to represent. Basically, we will compare the circuit metric with the reference value. So reference value here you can define a bit. Basically, in our system, we just use the average metric value of all the content of the qubits. So if it is much better than the reference value, so we will use blue color to represent it. If it is much worse than the reference value, so we'll use red color to represent it. And also the radius will also reflect this kind of difference. So here, basically, a larger blue circle means the qubit is has a better performance. The noise is relatively small. If it is like a larger red circle, basically means the noise is quite high. So this is about qubits. And also we have visualized the topologic collection of the circuits. So the idea is, we will collect the corresponding qubit by using this kind of vertical lines, and also the x coordinates of each qubit of each gate corresponds to its gate error distribution. So here you can see we will visualize the noise status of each quantum computer at each time step. So so for each time step, actually we will also provide users with an overview of the overall gate error distribution. So here you can see this part, we are using this kind of error chart to represent the overall gate error distribution. So it can be regarded as kind of like some summary of the gate distribution. You can align it horizontally. So for example, in this part we have some gate which has a very good performance, right? And at this part we have some gate which worse performance or a lot of noises. So here we use this kind of error chart to represent the error distribution of gates. So when the user want to see, what is our overall gate error distribution, they can directly identify it from this very straightforward and simple visualization. So by using this visualization, they can get overview of the overall temporal evolution of the whole quantum computer. They can also check the details of each time steps and also their topologic relation, topologic connection between different qubits. So this is for quantum computer selection and also visualization. And the next step is that we will, for example, after we select this quantum computer, then the logic quantum circuit will be can be transpiled to multiple physics circuit, even on the same quantum computer. So then the next step is, okay, which physics circuit is better? So it's actually difficult to fit even hundreds of compiled circuits regarding the corresponding quality. So the idea here is, okay, we will follow the previous design here. We use a consistent design. We will use this kind of blue color to represent better performance and or less noise, and the red color to represent worse and worse performance or a lot of more noises. And the horizontal coordinates corresponds to the depth of the circuit, because for a specific logic circuit, after it's transpiled into physics circuit, we need to check, okay, what is our depth of the circuit. So we also realize this kind of information. So for this part, actually, later Shaolin will show, okay, we can do sorting so that users can understand, okay, what is our depth of the circuit, and what is our noise level of this transpiled physics circuit. So this is a circuit filter review. And finally, okay, after we select, okay, for example, only a few, for example, 2 or 3 compiled circuit or transpiled circuit, we will we can further do detailed comparison to see, okay, which one is even better, right? To select the optimal physics circuit from all the transpiled circuits. So here we actually also explore some other alternative visualization designs. So here, let me just focus on the overall design. So as you can see, our idea is, okay, we will visualize both the noise distribution of the gates and the noise distribution of the circuits. So the idea is, okay, the bottom part of this kind of bars represent the matrix or the noises of different circuits. For example, here we have a 7 qubit, okay, 7 qubit. So each bar represent our noise metric of each qubit. And here we have this kind of black, I would say, gray rectangle. It represents our usage of these qubits across different transpiled circuits. So the color, the bar's height represent our usage in this specific transpiled circuit. So by visualizing this information, we can see the qubit usage difference between the current circuit and the our usage of all the transpiled circuits. And again, the color represent the noise level. And the upper part represent our noise distribution of the gates. So as you can see here, this gate is connecting to qubit 0 and qubit 1. Basically means this gate corresponds to the gate between qubit 0 and qubit 1, so which is also specified here. So similarly, we will we will show the usage distribution of each gate, and the color also corresponds to the noise level. So by using such a very straightforward and simple visualization, we can get a sense of what is our performance of this transpiled circuit. And if we, for example, select multiple transpiled circuit here, we can actually also do side-by-side comparison. So by using this way, the users can actually conduct in-depth comparison of different transpiled quantum circuits. Okay, so I will end up here. So for the subsequent part, I will hand over to Shaolin. So Shaolin will show some online demos so that you guys can get a sense of how our approach can really work, can really help users to get a sense about our noise distribution in quantum computing. So Shaolin, I will hand you the time to you. So maybe you can start share screen.
Okay. Can you hear me?
Yeah. Yes, you can start share screen.
Okay. Okay, Proof, can you see my screen?
Yes, you need to change it to presentation mode.
Okay. Okay. All right. So
Yes.
okay. Thanks, Proof. And next, I will show you guys a demo of our visualization system, and then I will conduct a hands-on practice of our system. And before we get started, we can take a look at the screenshot of our system. As mentioned by Proof 1, we have 3 views. And based on our workflow, we have two two steps. The first one is a quantum computer selection, and the other one is compiled circuit selection. So for the first step, the quantum computer selection, the view 1 here handles this kind of step, and view 2 and view 3 handles the compiled circuit selection. And you can see here is a control panel of our system, and you can interact with our system via this GUI. And before we get started, please note that the execution, the transpilation of our of the circuit and the noise data, all of this data and the compilation results were collected in advance to make the procedure more smooth. Because for a specific compilation, the execution time will even be hours. So we stored all of this data in advance to our database to achieve a more time-saving representation of our hands-on session and our online demo representation. Okay, so let's get started. Let's see. Okay. All right. This is our online visualization system, and you can see here. This is the view 1. I'm sorry. Okay. This is the view 1 of our system, and this is the control panel. Because the first step is to select the optimal quantum computer. So the view 2 and view 3 will depends on the quantum computer that you selected in the first step. So let's take a look at the control panel. So as mentioned by Proof 1, first we need to select our preferred quantum algorithm, for example, the QFT algorithm. And then we could take a look at all of these available quantum computer which were provided on the IBM Q platform. Because the QFT algorithm requires 2 qubits actually, which were less than, for example, which were less than the 5 qubits for the IBM Q Bogota, which means that for example, all of these quantum computer are available for the for our execution of the QFT algorithm regarding the number of the qubits we required. So we can take a look at all of these available quantum computer, and the bar here represents the QE number of this for this quantum computer. Okay, and from the nodes or from the circles, for example, this blue circle means that the readout error here are above the reference value, which is the average of the readout error of all of the qubits for this kind of machine. And you can see here, because I have a first glance of all of these circles, and most of them are blue for the quantum computer IBM Legos and IBM Purse. Most of them are blue. And for example, if I take a look at this quantum computer IBM Q Santiago, we can see that the qubit 2, the color of the qubit 2 is generally red, which means that the noise is always below the average, the average without the average quality of all of these qubits. So we can also see from the last segment here, for example, as mentioned by Prof. Wang, this last segments represents the connection of these last segments represent the connectivity of the actual or physical connectivity on the quantum computer, IBM Q quantum computer. And for example, this one here represents the gate acts on the qubit 0 and qubit 1, and the horizontal coordinates of all of these like segments denotes the gate error. Yeah, and the color map here, has a summation of the noise of all of these quantum gates. And we can see here from this colored histogram, we can see that from January 29th to February 12th, the performance of the quantum gates on the IBM Q Purse are generally not so good. But from after the February 19th, the performance will be very stable and performs well. Yeah. So let's say if I select the IBM Q Legos for my further execution, we can see here the label IBM Q Legos are shown in the control panel. Will be also updated, and from here we can set the time range and the interval of the for this real one. For example, the time range means that the starting date and the ending date, and the interval means that how often do I need to show this kind of time slice here. And the compilation times means that if I launch the compilation, how many compilation time do I need to compile for this kind of quantum algorithm? Because you know, every time you launch the compilation compilation result will be various. It's not the deterministic results. So here, if I set the compilation times 60 times, theoretically there will be 16 different compile circuits. Yeah, but there will be the results may be less based on the structure or based on the architecture of the quantum algorithm, and also the complexity of the quantum algorithm. So if I set this value to 16 as default, and then I click the compile button here, and you can see that there will be 16 compare circuit shown in the view 2. And as mentioned by Prof. Wang, the horizontal coordinates of these circles denotes the depths of the physical compare circuit. And each node represents compare circuits, and the color of it represents if the performance of this compare circuit is good or not. Okay, so from this chart, we can conclude that there will be maybe four types of compare circuits based on the circle radius, the color, the depths of them. Yeah, because you can see here this one, the transpilation compare circuit 1, 12, and 13. I mean, these three are the same, or they have the same structure, or they have same connectivity on the real quantum computer. And this, for example, these two or these 5 are the same compare circuits. So you can see here, you can interact with this visualization system via this control panel, and you can switch between the gate score and the qubit score. For example, we set the gate score as default because all of these compare circuits are rendered based on the gate score we calculated from the performance regarding the gate error rate and the for example the usage time of each gate. Yeah, because let's say a physical quantum gate, for example, the CNOT gate between qubit 1 and qubit 2, this kind of quantum gate will be implemented multiple times, maybe hundreds or even thousands, based on the complexity of the algorithm. So the usage time of this quantum gate is very important. Yeah, because if you implemented a quantum gate with a very good performance, it will be good. And if you implemented a gate which has a very bad performance, the overall quality of this compare circuit will be very low. Okay, so if I click this qubit score here, yeah, we can see that all of this compare circuit will be rendered based on another metric, qubit score. So this is the display mode, and for the score filter, this is for the exploration of this quantum of this compare circuits with different score, and you can select and filter the compare circuits of interest. For example, if I set the range a little bit higher, yeah, we can see that all of these compare circuits with good or high gate score will be remained in this view, and all of this bad performance bad performance quantum gate will be filtered out. And also, if I set to a lower value, yeah, you can see that there will be only this multiple quantum this multiple compare circuits with a very lowest gate score will remain in this view. So from this view, we can see that for example, the transpilation 1 is very good. So I click this one. Maybe this one could be used for my further execution. I don't know. I need to check this. I need to check it further, which I will show you later. And I click this one. These two are generally similar, but the gate score of this one, the transpilation 15th, is relatively or slightly lower than this one. And I also select this compare circuit for my evaluation of my idea or for the principle of our visualization system. Okay, for this three, if I mark it, I mark this transpilation 1, and then I click this run button here. Okay, you can see here, this one denotes the transpilation 1 compare circuits, just as this compare circuit shown, and the other two are shown here. So from this view, that we can see that the transpilation 1 is better, or the fidelity of it is generally better than these two, which is 16.8%, and the other two is around 15%. Yeah, the difference is very large. Yeah, so if you want to see more details of these three compare circuit you selected, you can turn on this probability distribution view, and I can switch between these three compare circuits regarding their regarding the differences between all possible quantum states. For example, for the better transpilation 1 compare circuit, the blue bar means that this is a execution results of noise-free, and the red one is the practical or the actual execution result you perform. So from this view, we can see that the state 101, the number of these shots will be over 600, and for let's say for this transpilation 15, yeah, the numbers of it will only be less than 500. So let's try another quantum computer for exploration. Let's say let's select this quantum computer, IBM Q Bogota, and you can see here there will only be okay, there will only be 4 time slots here, which is not very reliable from my perspective. And if I browse other quantum computer, and I found that the IBM Q Quito is which is the one I'm looking for regarding its let's say this performance of qubits and the performance of gates, and the QE number is relatively low compared with IBM Q Legos and IBM Pearls. So let's select IBM Q Quito, and I also click the compiled button. Okay, so there will also be 16 compiled circuits here, and I select these 3, which has a better performance regarding this gate score, and I also select 2 bad performance compare circuits here, and I also select this one for my further evaluation. Okay, and I click the run here. Okay, and you can see that this is not very stable. Yeah, because this one has a fidelity of around 16. Maybe due to the we select the gate score here, and the qubit score is not so good. But for example, for these two compare circuits here, we can see that the performance of these two compare circuits is relatively higher than the one I select for I select for the comparison. Specifically the transpilation 33 and transpilation 34. Okay, so this is a demo for the small scale quantum algorithm, and now let's have a try on the another types of quantum algorithm, which has a relatively larger scale, which has a larger scale. Okay, let's refresh it. Okay, so if I select Shor's algorithm, which has a relatively larger scale, and because this kind of algorithm requires more than 5 qubits, so the option of my the option of the possible quantum computer will be IBM Legos, Perth, Jakarta. Yeah, these three, because the number of qubits required for for my execution.
So sorry.
And I can see here. Okay.
Shaolun,
Yeah.
sorry for interruption.
Okay.
So could you, due to limited time, could you speed up your presentation and finish it within 2 minutes?
Okay. Okay. Yeah. All right. So based on the due to the limited time, I will end up here for my hands-on session. For my for my demo showcase session, and let's get back to our slides here. So I tried I just showcased several demos of how to use our online visualization system, and then we also conduct several evaluation to evaluate our visualization approach. For example, the case studies and several in-depth user interviews. And for the case studies, we invited 2 domain experts from the educational institutions, and we asked them to perform also the 2-qubit circuits, and another one is a Shor's algorithm. We asked them to perform this two kind of quantum algorithm, and we also asked them to perform the quantum circuit execution with noise awareness provided by the visualization approach of our system VACSEN. And furthermore, we also conducted the in-depth user interviews with 12 domain experts based on 9 tests provided in this slide. All of these can be categorized into 2 groups. The one is the quantum computer selection, which is T1 to T5, and the other one is compare circuit selection, which is T6 to T9. And we also asked them to rate for our system VACSEN, and they also provided us many very valuable feedback. to after using our system, and this is the results of the reading of our visualization system, which is regarding the effectiveness, usability, visual design, and the interactions. And you can see here they also provide some qualitative feedback, which can also help us to further improve our system. Okay, so I think you could you guys, if you guys are interested with our visualization system, you guys could conduct a hands-on session and interact with our visualization system via your own laptop or desktop. And we also provided some tasks for you to guide your exploration. Yeah, these five points are for the quantum computer selection, and we also provided you 4 points for the computer circuit selection.
Shaolin, you can skip this part due to limited time.
Okay, yeah. So if you guys are interested in it, you could conduct this kind of hands-on session after we end up this presentation. Okay. So in conclusion, we provide a online visualization system VACSEN to facilitate the noise awareness in quantum computing. And we also provided 2 novel visual design, the circuit-like design and the couple bar chart for you to support a very detailed quantum computer selection and the compare circuit selection. And we also open sourced our code. We also make our system publicly available for the general public or the users from quantum computing to access it and use it. Okay, so okay, this is the presentation of our paper VACSEN, a visualization approach for noise awareness in quantum computing. And if you are interested in our work, you can access the URL provided in the below of this slide, and you can also scan the VR code to explore more about our work, our group, and our research topic. And if you are also interested to collaborate with us for your own idea, we can have you can contact me and we can have a further discussion of the future possible research direction. Okay.
Okay. All right. Yeah. Thank you, Shaolin. Yeah. Thank you.
Thank you.
Okay.
So
great.
I have already shared our link in the Zoom chat. If anyone is interested in explore the system, feel free to click the link we have provided in the Zoom chat. Yeah. Okay. Thank you. So I think maybe due to limit time, we don't have a Q&A session. If you guys have any questions, just drop me an email or drop Shaolin an email. Yeah, I will hand over the time to Weiwen. Yeah, Weiwen.
Sure. Thank you, Dr. Wang, and also Shaolin for the great presentation. Okay, so maybe Shaolin, can you just stop sharing, and I think we will have our final end session. Great, thank you. So okay, so for now, actually, we have already seen a lot of details of this tutorial, and let's go back to see what we have seen. And for the first thing, actually, this is the tool used in this tutorial, and also this is a website for this tutorial. And if you want to access any resources, actually, you can directly scan the QR code, and also you can see from this website we provide the slides and also the resources for the code lab, for the GitHub, and also for the visualization tool. We have the website and the platform. So I think this will be the most easy way for you to access all of these resources. And Oh, so let us have a quick overview of what we have already talked today. For the second session, what we do is that we introduce the quantum flow, which is a co-design framework to enable the neural networks on the quantum computer. And also we demonstrated that it is possible to reduce the complexity for the neural operation from order of n in the classic computers to order of polynomial log n in the quantum computers with some specific kind of assumptions. And also in the experiment, we demonstrated that the proposed quantum flow can achieve the same accuracy with a cost reduction of more than 10 times over the classic computers. And for the third session, actually what we introduce is about the first framework for the quantum neural network compression. I believe this is the first work in the research area to bring the compression technique to the quantum neural network. As you can see from this figure, the above ones are related to the quantization and pruning in the classical machine learning, and the below one represents the stuff on the quantum machine learning, and they have they have the fundamental difference between both the pruning and the quantization in terms of the cost. And in our result, we demonstrated that with a dedicated design of the compression technique for the quantum neural network, actually we can reduce the compiler the quantum circuit length for more than 2 times reduction without accuracy loss. I think the circuit length reduction is very important because in today's quantum computer we have a lot of noises, and the noise will be accumulated along with the increase of the circuit length. So that when we reduce the circuit length, actually it automatically help us to increase the fidelity of our design algorithm. And this work was has already been accepted by ICCAND, and it will be represented on November 2nd. And in our fourth session, actually we go overview the visualization tool, which can provide the users the sense of the noise of the quantum computer and different days, and also this will help users to see which quantum computer backend we want to use to deploy our final application. I think this is also very important, because if you do not have any sense of the noise at the current state quantum computer, actually you cannot deploy your algorithm to the correct quantum computer. This is also because the noise in the quantum computer actually changed every day. So we cannot assume that if we want to design an algorithm for one backend, and we can consistently run the algorithm on that backend. So I think such kind of realization tool is very important for the users to have the sense to which quantum computer we can use. Okay, so put all things together, actually we formulate such kind of design stack. Actually, I think this is also introduced at the very beginning of this tutorial. We discussed about the thing what will be the best neural architecture for the quantum computer, and also we are talking about we have already talked about what will be the best quantum circuit design to support the neural networks. We also demonstrated it has the potential that we can compress the quantum neural network and also achieve the same or even better accuracy, because we reduce the quantum circuit length, we improve the fidelity. And also, as you can see, by integrate all things together, actually we formulate such kind of design stack. For the software layer, we have the network exploration to help us to design the neural network for the quantum computing. We have the compression to do the optimization on the model. We have the library, we have the visualization tool, and finally we have the device-aware design, so that we can find the more robust neural network. And move forward, actually, let's see the remaining challenges and also our outlook for the research in the quantum computing, in particular for the quantum machine learning. The first thing is about the encoding. As you have already seen in our quantum flow design framework, actually what we do is that we try to encode the classic data to the quantum computer, so that we can perform the classical machine learning task on the quantum computer. So I think this is one way in today's research what we do, because a lot of data we have for the machine learning is they are in the classical format. So we need to encode the data first to the quantum computing. But such kind of encoding itself can easily become the bottleneck. So our outlook for this direction is that maybe the other techniques like the quantum sensing and the quantum memory can help a lot to solve such kind of problem. And if we have such kind of devices, actually we can directly process the data in the quantum quantum world. We do not need to do the conversation between the classical world and the quantum world, so that we can encode the data to the quantum computing. And the second challenge is nonlinearity. Nonlinearity is the key point, the key element in the machine learning algorithm, in particular for the deep learning, for them to achieve success. However, for the quantum computing, a lot of operations, not a lot, actually all operations in the quantum computing are equivalent to the linear function because it is based on the matrix multiplication, a matrix and a vector multiplication, and the matrix itself is a unitary matrix, and they are equivalent to the linear functions. So our outlook is that we have two ways to solve that kind of problem. The first way is that if we have some hardware to provide the efficient interface for the measurement and encoding, that will be great. Another way is that maybe we can have some novel design like what we have done in the QuantumFlow. Instead of directly regard the neural network as unitary matrix, actually we can smartly change the encoding of our data so that we can apply some such as random variables in the QuantumFlow to represent the nonlinearity. So I think these 2 points are related to the how can we make the learning on the quantum system become more better. And the third one and the fourth one will be more related to the to today's quantum computer. And the first one is about the noise. As you know, for today's quantum computer, it still has a very large noise. For the classic computing, the noise level is around 10 to the power of -15. But for the quantum computing, the noise is 10 to the power of -2 to the 10 to the power of -4. So there are a lot of noise in the quantum computing. So one approach that we have already done is that we make the visualization tool to provide the error information to users so that it can help user to identify which quantum computer we want to use to process our task. And the second technique that a lot of people doing in the quantum era is quantum error correction. So that people want to use multiple qubits to perform the error to perform the error correction. And one opportunity here is that for the quantum machine learning, for the learning algorithms, actually we do not need the quantum computer to have to provide a perfect qubit. That is, we can we can fully correct the error. But in that way, if we want to create the perfect quantum bits, the qubits, actually we need hundreds or even thousands of logical bits. So that has a very high overhead. Instead, if we consider the learning, if we consider the learning application, actually we do not need the exact the correct answer. Actually, we just need our final result to reach some threshold. Therefore, it provides us some opportunities that we can create the quantum error to some degree instead of create the perfect qubits. So this is our thinking about how can we combine the noise and the quantum learning algorithms. And the last one is about the scale. For today, we are still talking about the intermediate scale of quantum computers. But you can see for the today's quantum computer, the scale it scales up very rapidly. For the IBM, it only takes 5 years for them to scale from 5 qubits to more than 100 qubits. So when the quantum computer scales up, when we have more than hundreds of quantum qubits, how can we perform the quantum simulation? This is also very challenging because the simulation at this stage is also a very important powerful tool to validate whether our design is correct or not. Because the quantum computer itself has a lot of noise. We cannot validate our design by directly running on the noisy quantum computer. So we believe that the simulator itself is also very important. And our outlook on this point is that maybe we need some specific design on the hardware so that we can we can speed up the simulation, or we may apply some machine learning to perform the predictions. This is really also related to the machine learning for the EDA. So I think there's also some opportunity here, so that we can overcome the large scale for the simulation. Okay, I think we are almost run out of time, and if you have questions, maybe we can take this. We can take one to two questions, and also I think here in this page we demonstrate the website to access the resources. So maybe we can stop here, and if you have questions, we can take 1 to 2 questions. I think okay, questions. So for our online audience, do you have any questions? Maybe you can put input your questions into the chat box.
Yes.
Hi, Guan.
Hey.
This is Dr. Qiang from Shanghai.
Hi, Dr.
You mentioned in your final talk talking about the quantum simulation, right?
Right.
What do you mean simulation here? You mean simulation on quantum computers or classical computers?
Thanks for pointing this out. Actually, here we talk about the quantum circuit simulation. This is not like the simulation of the physical phenomena. So what we talk is that actually in our first session we demonstrated that for today's classic simulators, actually it can even we applied the supercomputers, actually we can only simulate up to 50 number of qubits. So when the quantum computer scale up, like today we have the IBM quantum computer with more than 100 qubits, how can we simulate the quantum circuit on such kind of scale of quantum computer? I think it's I think this self is a big challenge for today's quantum simulation, quantum circuit simulation.
So I just want to clarify that in the final tutorial session, there is a visualization tool, right?
Right.
And that visualization tool is to visualize the quantum circuits on real quantum computers. Is that correct?
Yes, that is correct.
Right. So but the number of qubits, Weiwen talked about there are two types of quantum circuit. One is less than 5 qubits. Another is more than 5 qubits, right? But he didn't mention that how many qubits that tools can maximum limits to. How many qubits it can visualize, simulate?
Oh, I see. That is a good question. So, Dr. Wang, do you want to take this question? You are muted, I think.
Yes, yeah. I think this is actually a really great question, and it actually corresponds point out one of the future research direction we can work on. So in our system, VACSEN actually I think is proof of concept. I think is a first visualization system to have quantum computer users or researchers to cumulatively explore the noises in quantum computer and the corresponding transpiled quantum qubits, quantum circuits. So for this part, in this current system, actually we're mainly focusing on the quantum computers with like maybe less than 20 qubits. But we know actually, with development of this quantum computer, I think there will be more and more quantum computers with a lot of qubits, like maybe 700, so on and so forth. So when we trying to explore those kind of quantum computers, I think probably our system, especially this part, computer evolution view, it will suffer from this kind of scalability issues. But so for this,
okay, but I just want to know more. Okay, is that your visualization is really wrong on those 5 quantum computers, or you build a model, like some model in your database model that you simulate the quantum circuit?
Yeah.
Or really run those quantum circuits? I mean, really run on those computers, on those quantum computers. So your limitation is that quantum computers can provide you, right, with how many qubits that you can run. Is that correct?
Yes. Yeah. So for this part, actually, this is actually an intact system. In our backend, actually, we were directly connected connected to the IBM quantum computing platform. So in our backend, we will run our circuit in the backend, the IBM quantum platform. So this is we really run it on those platforms. We have because this cloud computing platform that provide this API, we can really write code and run.
IBM allow you to run.
Maybe I can take this. I can take this question. So for today, actually, IBM provide different different levels of for the access, and for the public, actually, the maximum number of qubit can be accessed will be 5. And if we are in their program, like the education program or research program, actually the maximum number of qubit that we can access will be 7. And okay, so this is a second level. And for the last level, actually, I think there is one thing called the IBM Quantum Hub. And if we are in the IBM Quantum Hub, actually the number of qubit can be accessed will be 120.
My really tough question is, okay, my really tough question is this. So this is really constrained by some third party, right? IBM constrained the maximum limits you can run. Okay, will that make you feel some kind of you want to have some kind of more qubits to run? Even IBM does not allow you to run on its computer directly, but you can build some model so you can simulate more qubits to run, something like that.
Yeah, actually, I think that is a good point, but there is a lot of difficulties. Actually, one of the most difficult things about the noise. Actually, in order to do such kind of thing, actually, what we need is that we need a very accurate noise model. But you know that even for the IBM quantum computer, actually they do the calibration of the data for every day. So that means the noise in the quantum computer itself is actually changed every day, and the change itself is not in a fixed or followed some distribution. It has a lot of randomness inside it. So I think this will be the largest challenge in order to build a model for the noise for the quantum simulation.
Yeah, okay, that's the end of my question.
Great, thank you for the question.
Thank you.
Thank you. Hi, Weiwen. Hi, this is Dr. Qiang here. So the question is, so the simulation results will actually really depends on which quantum machine you're using to do the simulation, right?
Right.
To
visualize it. Yeah.
The error model.
Then what kind of error model? Do you need an error model for each different kind of different quantum machine, or what? How can you handle this issue for the errors?
Dr. Wang, do you want to take this?
So your question is about what kind of errors? Yeah, what kind of errors will be considered in this visualizing system? Is that a question? Let me double check. Okay, so for this part, I understand maybe there can be different metrics, different error metrics. So for this part, I think we just pick up the most popular and widely used, we can call it calibration data provided by IBM cloud content cloud platform. So I think this kind of metrics probably has been widely used. But I understand maybe there can be some other error metrics on. So first, for those kind of metrics, for actually, if necessary, we can further incorporate them into our system. So here, of course, we cannot, we do not include all the potential error metrics. We just pick up the most popular ones. So it is possible for us to extend to other metrics. And as we have shown in the VA system, actually, we can allow users to interactively select the matrix. For example, here, like I just mentioned, for example, here we have we are now using for the readout error T1, T2, and the get errors. But in the future, if it's necessary, actually, we can further incorporate other error metrics if possible, if necessary. So this part, we can allow users to interactively select which metrics they want to explore. Yeah.
Okay. Yeah, that's great. You did a great job, and you all guys there in the tutorial did a great job today. Thank you very much.
Yeah, thank you for the question.
Okay, thank you for all these questions. I think that will be the end of the session. Thank you for attending.
Thank you. Bye.
Thank you.
Bye.
See you guys. Bye.
Bye.
李乔，来。
Hello.